All right, great. First of all, a very happy new year to everyone. This is Jaimin Patel. I'll just introduce myself in a bit. So by the way, welcome everyone to the training that we are going to start today, which is on Spark and Scala. I think some of you I have already known because you all have, I think been part of the Hadoop development course. So I know a couple of people here. But I think few of them are new to me, and in fact, I am also new to them. So it's okay. I would say an opportunity to know each other. Anyway, so first of all, again, a very warm welcome to this class, and let me just introduce myself before we get started. This is Jaimin Patel. I have about 12 years of experience in the industry, and for last 4 or 5 years, I'm working on big data. For last 1 year, I have worked on a product which uses Spark and Scala extensively. I have basically been working as a consultant and provide solutions to many corporates. I do a lot of consulting, and apart from that, I also do a lot of corporate training. So that is one of the reasons why we are meeting here. Right. So I have trained about 2,000 people across the globe for last 2 years, and yeah, it's like people from different parts of the world I have met, I have learned from them, as well as I have shared them. So that's a brief introduction about myself. What I would now do is I'll first introduce you to the entire course content and what we are going to do as part of this training. So we'll just walk you through the agenda first, and then we can get started from there. All right. So let me just share my screen. All right. So is everyone able to see my screen? Okay, great. So let me walk you all through the course overview of this training, what we have planned for you. So basically, the course objective for this training is after completing this course, you will be able to learn these topics, which are, will understand how to install Spark, will understand different features of Scala. Before we get into the Scala, in fact, we do a lot more, coverage on batch analytics and real-time analytics with respect to Hadoop and Spark. And then we'll all obviously get into the details of Spark architecture, discuss how to use RDD for creating applications in Spark. We will also understand different ecosystem components of Spark, which are Spark SQL, Spark streaming, Spark ML programming, which is machine learning libraries, which are written in Scala, which are compatible to be executed on Spark. And then we will also talk about graphics programming. So there is a component called graphics, which will understand and how it can be used with Spark. So these are the overall topics that we should be able to cover. So by the way, I'll also formally introduce these topics. There are slides available for that. So there is basically a prerequisite for the target audience. By the way, anyone and everyone can attend that course. There is no real prerequisite as such. But of course, people who are aspiring for a career in growing and demanding field of real-time analytics can get benefited from this course, right? Apart from that, anybody who is working in IT with various professions can join this course and can learn, gain thorough understanding on Spark. As I said, prerequisite as such, no strong prerequisite, but yes, there is definitely a good to have prerequisite for the people. One of the important stuff is fundamental knowledge on any programming language. It could be Java, it could be C++. I would request to have a working knowledge on either Java or any other object-oriented programming would be beneficial. Basic understanding of any database. Normally, if you understand how to write SQL queries, more than enough. Okay, you don't really need to get into procedures and PLSQL or complex query execution and optimization. If you can understand basic SQL queries, that is more than enough. And of course, working knowledge of Linux and Unix-based systems. Again, it's not a mandatory requirement, but it's a good to have a requirement. Okay, so that's the course prerequisites that we are going to that's something that people should understand, and if you don't have it, doesn't really matter much. But I would request, if people don't have any programming background, you should also parallelly start working on some of the programming language. For example, take Java and try to understand few basic concepts of Java. Okay. Now, just give me 1 minute. I need to also open one more slide. Just give me 1 minute. All right. So as I said, let me first go through some of the introduction PPTs as well before we get into the conceptual details of Spark and related components. So as you can see from here, it's just for your information. We just introduce it to one time. So I'm sure you would have already browsed about that, but this is about what Simplilearn provides. It's actually definitely world's largest certification training destination, and it has been doing training for last 5 years. As you can see, they have actually expanded it to the various parts of the world. Just one second, I got a comment from Satyanan. He can't hear me. Can anybody? Is everyone able to hear me, or is it the same with everyone? Yes. Okay. So looks like others are able to hear. Okay. Cool. Yeah. So I was just going through the introduction slides of Simplilearn, and as you can see here, there are various courses that are being provided, and I'm sure you would have already gone through some of the other trainings as well. It's for the people who are joining for the first time. You can get training, certified training programs in all these areas, which you can see here, right from project management to quality management, virtualizations, cloud computing, big data, of course, and related analytics technologies. So lots of technologies they provide training, and they are providing all these accredited certifications, as you can see on the below screen. And of course, all access online classroom pass. I'm sure you would have got these details from the Simplilearn team. So you actually get access for one course, and that's like one pass which you can use it for joining other courses as well. All right. So you can get more details from the Simplilearn team on that, like how to use that. But there is a 90-day access pass which is available. So for 90 days, you can actually enroll for one course, and then you can actually use that for joining any other course as well, right? Definitely, there will be a lot of support and technical support available from Simplilearn team. You can get 24/7 support. Just need to send email to the right email ID, which is getcertified@simplilearn.com. So that's the support email ID. You can just post any of your queries to them with respect to video recordings, or with respect to session links, or even if you need any technical support, they'll be the one who will help you on that. Just for your information, Simplilearn is also working on providing one team who are technology-wise expert team who can support participants in their technical queries as well, right? Because all the time it is not really possible for trainer to get into the problem solving of every people all the time. Once the training is over, it becomes difficult to kind of solve all the queries. So what happens is they are coming up with a separate team who's dedicatedly working on that. That's yet to happen. It's not yet ready, but there is one team which can which is available as a technical support team, which can solve your problem. But they are actually coming up with a domain and subject experts in that, so that it will be more that the response time is faster to all your queries. I'm sure you all know about LMS. If you don't know, there is a website which called lms.simplilearn.com. So you need to log into that website, and you can actually access your learning management systems. I'm sure you would have received your credentials from the Simplilearn team. If not, please talk to support team. They will get you the credentials. Okay. All right, I got a query from Ganesh. He says the voice is breaking in between. Is it true for everyone, or am I audible fine with others? Okay, so looks like Ganesh, looks like others are able to hear me fine. Probably you need to check your bandwidth. Sure, yeah. Cool, yeah. So again, you need to log into the LMS, click on My Courses tab to view the list of courses that you have enrolled for. You can click on My Test to view the list of simulation tests which you can do for practice purpose. And of course you can actually know how to kind of begin the training by choosing the course and test tab. Raise a ticket through help and support for all your queries. So these are the easy steps to get in touch with any Simplilearn support team for any of your queries, or to access all the materials which is available on your LMS. So I just want to tell one thing to everyone, that any queries with respect to video recordings, please raise a ticket to help and support team. They will get you the answer. By the way, normally you get your recordings in 24 hours of time, but if you don't get it by then, you can always post your queries to support team. And all the materials with respect to this training should be available in your LMS. Okay, everything is available in LMS, so there is no need to go anywhere else to find it. You can just go through your courses and you get all the materials available. If it is not there, again you can raise a ticket to support team and get it done. Okay, so there is recording on how to kind of access that, how to as you can see here, I mean, I'm just playing that recording, which basically says how to enter the the LMS page, and then click on different tabs here, which talks about how to get into the courses. As you can see, click on my courses, and once you are done with that, you can click on the my test to see all the simulated tests for the particular course. You can also start the test by clicking on that test tab and just say begin test to get the test. And of course there is a tab which says help and support if you want to raise any ticket. So that's how basically you use your LMS effectively to get any queries or I mean basically to get any information. All right. So we are showing it for the first time just to make sure that everyone understands what needs to be done when they need any information or when they have any trouble in accessing the course. Yeah, there is one more thing which is basically accessing various e-learning resources. So you can just check view all topics, which basically shows you how to access different courses as well, which are available on a particular course, all the topics for a particular course along with different lessons. Most modules have chapter quizzes that you can take to review your learning. So all the modules, in fact every course will have different lessons, so you can click on one lesson, go to that PPT, you will have some questions and answers like quiz, as you can see from here, which basically helps you understand how to it's like you learn something and then you just answer those quizzes to kind of recheck your learning. That's it. And there is a download center where you can download the materials. Okay, so I'm sure you are all familiar with that part, and people who have already registered for other courses. Any keynotes you want to keep track of your progress, you can do it in the notes section, right? So that's just basically a guide to your own learning. And of course, last point is the Simplilearn community, which we have been recommending to all the people. It's actually an active community where you post your questions. Depends, sometimes you get your answers quickly, sometimes if during those leaves, these holidays, I think people were kind of not very active on those communities, so you may get time to get your response back. But it's fairly active community, and a lot of people are there who can help you answer your questions apart from the subject matter experts. So even we join there, and whenever we have time, I answer those queries. So it's like whenever you have time, you log into that. You can see all the questions that are asked by people. It's mostly an interactive community learning, so you can also answer some of the queries that other participants has asked. Right, so that way it's a good interactive community. So you can use that. There is a link provided here. Just join it by clicking on that. That's about SimpliTalk, hassle-free interaction with the trainers, course-wise, the direct interaction with fellow participants, and of course, a good way of sharing your knowledge with the people. All right, so that's about the Simplilearn introduction slide which I wanted to cover. Yeah, there are some ground rules which I would suggest people to follow. It's not a very hard and fast rule, but it's a good to have thing. So participants are requested to use chat window whenever you want to post any questions. So let's try to be uniform. So everyone who wants to ask questions, just use chat window to ask questions. So that way it's easy for everyone to kind of get into this. And I can actually just use one window to answer everyone's question. So that will be better for me also to manage that well. But however, it's fine. I mean, sometimes I'll be very flexible, so don't worry about it. In case if you want to speak up, you can let me know. I can unmute you, and you can ask your questions. So I'm perfectly fine with that. And don't worry about those break times which are written there. So we will have break times according to our coverage. So when we come to one logical covering, I mean, when we complete one point or topic, then we will have a break. So it's better to kind of keep it that way so that people are benefited with whatever we are learning. All right, so that's about Simplilearn introduction. And then yes, let me now get back to what we are going to learn, which is of course Spark. We all know that. So there is one small case study which was used here in this PPT, which helps us understand, right, what kind of value that using these technologies like Spark can provide to the business. So value to professionals. So there is a case study which is from the company called Ooyala. Okay, Ooyala is a video streaming services company which offers services to various media organizations. It offers actionable analytics on top of that. So they actually scrape data of different media, basically a media data from different organizations. They use that data to come up with actionable analytics, and they send that, or I would say basically sell these analytics to the media organizations and enable them to optimize their delivery standards for maximizing their revenues. Okay, so it's kind of a company which streams the data and then basically do some analytics on top of that and sell that analytics to help them decide better to increase their revenues. And of course, they do like processes of this data and achieves more than 2 billion analytics events every day. So that's the the fundamental I would say functioning that is being performed by Ooyala. That's the whole objective of this company, and that's what they do on a daily basis. Now, initially the problem for them was deliver intelligence in real time by mining this stored data in a faster manner, right? Which was a problem for them because they were not able to achieve that with the of course the technologies like Hadoop. They were able to do it better, but not so fast. And they had a need of real-time interactive SQL query, and they wanted to make MapReduce faster. So this was the need, and hence they moved on to Spark. So this issue has been resolved by using Spark. So Ooyala can now perform real-time analytics using it, expand rapidly, and offer real-time intelligence based on huge data sets. So basically, this case study was, I mean, we don't really have anything to learn here, but what we are trying to highlight a point is we just took a real-world case study just to emphasize the fact that now business is also seeing benefit by using Spark as a technology to do analytics on top of the data compared to the traditional technologies which were used so far, right? And that is basically Hadoop MapReduce. Sanjay, let me repeat this. I can understand your question. So in case if you don't find any PPTs in your LMS, I will not be able to share anything. It's you need to raise a ticket and check with support team. They will help you in doing that. They are pretty fast in responding to that. So just raise a ticket. You will get your answer in 24 hours of time. Okay. All right. So let me continue. I hope Sanjay you got it right. Okay, so this is how we have structured our training. Okay, course overview, we have just done that. We'll start with introduction to Spark. Of course, that's the base, and we all want to know what is Spark and how it works, how it functions. We'll do some programming in Spark first, so that in the lesson 1, I would also cover a lot of other things which are not there as part of this PPTs, because it's very important that you first make sure you actually clear all your basics. Once you are very strong in the basics of what is Spark, why it is required, why it is faster than MapReduce, your 70% job is done in learning Spark in the lesson 1 itself. Trust me. Once we complete lesson 1, I want to make sure that everyone understands the core of Spark. And after that, it's all beautifying it, how to use some advanced concepts in Spark, and how to use, SQL on Spark, how to do streaming on Spark, how to use machine learning, graphics, which is all fine. But then the core of Spark is the most important thing, which everyone needs to understand, right? So we'll be spending a lot more time there. Okay, and I would also cover some of the stuff which are not there as part of this PPT, just to make sure everyone understands that as well. Yeah, so once we cover that, we will get into, so I would we will definitely cover all these concepts, but I just want to highlight one point, and I'm sure people who have already gone through the trainings which I take on Hadoop and other stuff, they would know my style, that I don't really follow all the PPTs step by step. I actually cover everything, but then I cover it in a flow, logical flow, which is more relevant. So after lesson 1, I would cover lesson 3, okay, which is very much related to core Spark. So these two have to be covered in detail, which we will do it. Then we will get into the Scala part. Scala is a different concept, or I would say different programming. I mean, it's a programming language, but it's a different topic altogether, which is not related to Spark. A lot of people think that Spark means there is Scala involved in that. Yes, it's a programming language, but it's separate language altogether. You can use it for lot of other stuff with lot of other frameworks, not only with Spark. So we'll learn right from basics of how to program in Scala, and do a lot of stuff in there as well. Once we complete that, then after these 3 lessons, we are good with Spark core. So we will basically get into the Spark SQL. We'll understand how we can process structured data using Spark SQL. We'll also understand how it is more compatible with Hive and what is Shark and all that stuff. Then we'll get into the Spark streaming, where we'll understand. Just one second. Yeah, we'll get into the Spark streaming, where we'll understand real-time analytics of the data. So by the way, there is also one concept that, I would say one thought process everybody will have. When they talk about Spark, they always talk about real-time analytics. It is true, but it is not entirely true. Spark is not just for real-time analytics. It is, in fact, it can do both batch as well as real-time. Okay. So Spark streaming is one component through which you can achieve real-time analytics on Spark, right? But Spark core is actually for the batch analytics, as well as it can support real times as well. Spark ML, again, it's a machine learning library for Spark, and Spark graphics is for creating graphs using Spark in a distributed manner. So these are the lessons that we are going to cover. We have ample amount of time in this training where we can cover all this with a lot more details and lot more practicals. So let me start with the first lesson, which is introduction to Spark. Okay, before I get into that, I just wanted to understand, anybody has any questions as of now? Anybody wants to share any information before I get into the first lesson? Okay, Satya. I will share one book name with all of you. You can just use that. It's a good book for Spark to start with. This is the book for Spark. Okay, and I'll be also sharing one white paper on Spark, which is very interesting. Document. You will actually learn a lot more on Spark just by referring that white paper. So I'll be sharing that as well. I'll just email you on that, so you can just go through it. I cannot share this book for obvious reasons, so you need to purchase it. Yeah. Any further questions anybody has? Okay, cool. So let's move forward. So let's start with introduction to Spark. So we are going to learn this on this course. We'll describe the limitations of MapReduce in Hadoop, compare batch versus real-time analytics. So that's the most important part that we'll talk about, and then later we'll understand the different features of Spark, architecture of Spark, and we'll install the entire Spark as well. We'll understand like how to set up Spark cluster on a single node cluster. And compare Spark with Hadoop ecosystem. So evaluation of distributed file system, then we'll talk about new distributed file system, what are the limitation of MapReduce. And as I said, I don't really follow PPTs too much. So let me use a whiteboard. So let us understand a couple of things which are building blocks for Spark. So first, let me explain you. So since here we talked about evolutions of distributed file systems, we want to understand a distributed file system. How many of you have already attended Hadoop training? Is there anyone who is not aware of Hadoop at all? All right. So looks like most of you have attended that training. So that is good actually. Yeah, I did not get enough responses, but it's fine. I'm assuming that people are fine with that. But what I would do is I would cover some basic concepts just to brush up everyone's memory, just to make sure that everyone is on the same page. Okay. So what I would do is, let us understand first some basics of distributed file system, okay? And I would also cover how data gets distributed. We'll just quickly see one important concepts on that, and then we'll get into the MapReduce. The reason why I want to cover some basics of this, even though some of you already know that, just to make sure that everyone is on the same page. And it is very important when you're comparing Spark with MapReduce, you need to first understand what MapReduce has to offer and why Spark is better than MapReduce, right? So when we want to compare it, we need to know both. Okay, so evaluations of distributed file systems have started based with the the analysis on the data size, which is basically earlier in late 1990s, the data volume was very less, but then over a period of time the data volume has been increased. So if you can see here, the data volume was very less in this period, but then from early 2000 onwards it's been growing exponentially. So initially people used to have a single machine, as you can see from here, single machine was used, but from that point onwards, when they started getting more and more data, the single machine or a computer was not enough to store that huge data. So they had a challenge first of all to store that data somehow in multiple machines. So that's the reason where they started using distributed file system concepts. Okay. So distributed file system concepts have been evolved from that point onwards, where people wanted to store big data in the systems. So let me just show you what is DFS and why distributed file system is important. Okay. Some of you who have attended my course, probably it's a repetition for them. So let us understand why distributed file system. Okay, so we'll just compare two different scenarios. I have one physical machine where I am having 4 I/O channels and 100 Mbps speed. That means 4 hard disks, and each hard disk has 100 Mbps speed to read the data or process the data. Now, if I store 1 terabyte of data in the single machine, what happens? I mean, let's assume we have a storage to support 1 terabyte of data in a single machine. And then if I want to process it, how much time it takes to do that? So it takes about 45 minutes of time. There is a formula available. If you put all the values, then you'll get 45 minutes. Let's not worry about that formula. So time to process 1 terabyte data in a single machine is 45 minutes, which is huge. So what they have done, they thought that let us use 10 different machines and try to distribute this 1 terabyte of data in all these 10 machines. Some part of the data I'll store it in every physical machine. Okay, and that's where and each machine being the same configuration, 4 I/O channel and 100 Mbps speed. If I store all the data like this, I can actually process the data, parallelly. So now time to process 1 terabyte of data in a parallel manner is reduced to just 4.5 minutes compared to 45 minutes of time. Right, so that's the performance improvement that you can get over a single machine storage. So this is the fundamental reason why distributed file systems are used. That's the most important advantage that DFS provides. All right, there are other advantages as well, but this is the fundamental reason why DFS is used. The reason why we are talking about distributed file system, because any framework, it could be Hadoop, MapReduce, or it could be Spark. They are distributed computing framework, but they can compute or process the data in a distributed manner only when it is stored in a distributed manner, right? So they work well and they provide better advantages when they are used with distributed file system storage. right? So Spark can function very well when it is trying to process a data which is stored in distributed file system, and same goes for MapReduce as well. But of course there is a difference in MapReduce and Spark in terms of the way they process data, which is why one is better than another. Okay. But the fundamental layer is, I mean, in terms of storing the data, is distributed file system. So that's why let's try to understand basic building blocks of DFS. So this is the advantage of distributed file system. So what is exactly distributed file system, by the way? So any distributed file system is a master slave architecture. As you can see here, you will basically have one master and multiple slave machines, right? And I'm sure all of you who have used or who have gone through Hadoop training would know, what we call as master, like name node and data nodes and all that stuff. So basically, for a distributed file system, there is a master, right, and there are slaves. Okay, and of course there are different other processes also which helps you to kind of do those checkpointing and everything, which we don't want to get into the details right now. So let's say I have a file which I want to store in this system. Okay, this is basically, so when I say distributed file system, what is it? There are 5 physical machines which are connected over a physical network. And every machine, as you can see, will have its own local file system, right? When we say local file system, they are all, let's say, Unix OS. All machines have Unix operating system. So they will have root, and then there is a home directory or user directory or whatever, blah, blah, blah. So there is always a physical file system available with every machine which you have, right? Which is called a local file system for that machine. And all of these machines are connected over a network. So there is no DFS here. No distributed file systems are available here. But we need to install the distributed file systems. What we do, we install some programs which makes up this DFS, which is basically, in case of Hadoop, we use name nodes and data nodes which are nothing but Java processes or Java programs which we install on these machines. And of course we do some configurations on different configuration properties to make them work as a master and slave and talk to each other. Now once you install these programs on this machine, it actually kind of give you one virtual layer, which is referred as distributed file system. Okay. So these processes or these programs which are running on a different machines are basically a Java processes which makes up the entire virtual file system, which is called distributed file system. So DFS is actually not a local file system or a physical file system. You don't have any storage, physical storage, which is called distributed file system. It's a virtual storage. Okay, it's a virtual file system. So where does data get stored? So when let's say you have a file of 1 terabyte, which I want to store it. As a user, I will use some DFS commands, and I'm sure you all know that Hadoop, there are different Hadoop commands you can use, like Hadoop fs-copy from local or put, and you just give your source location of the file and destination location of the file, and it will basically get copied there, right? So now the destination location is basically any path. It could be, let's say, under user directory, I want to create, let's say, a Spark directory where I want to copy the file. Now this is a virtual path. This destination path is a virtual path. Source location is the physical location where this file is available. Okay, and destination location is a virtual path, which is a HDFS or a distributed file system path. So when you execute this command, behind the scenes what happens, I'm sure we all know, we have gone through the right architecture, which explains us that behind the scenes it is going to divide your file into multiple physical blocks, okay, of 64 MB. In the latest versions of Hadoop it is 128 MB by default. So it divides your file into these many blocks, and these physical blocks are getting stored in each of these machines. right? Internally. We are not aware of that. They are being basically stored physically internally into this system. Okay. So as a user, it's completely transparent. We don't know where it is actually stored. We just think that this is the location where the file is being stored, but in this location is just a metadata. So what master does, it remembers that okay, if this file name is, let's say, f1, so just say this file is stored under /user /sp /f1.txt. This is the file, and it is basically, this is the location of the file which is being stored, which is being converted into these four blocks: A, B, C, and D. And of course, it also stored the location of every block. A is with data node 1, B is with data node 2, and so on and so forth, right? So this is called metadata information, file to block mapping, and the location of the file with the block, and which block is stored in which data node location. This is the information which is stored with the name node, which is a master in the distributed file system. So basically, this is just a virtual path. Physically, your data gets stored internally, and the same way when you read the data, whenever you just use this command like Hadoop DFS -cat and just pass this path, it basically goes to the master. This command becomes a client. It actually talks to the master and then get all the required block information and try to read these blocks from different machines, right, which can be presented to the user. So that's how we read the data. So we again give this virtual path where we think that entire file is stored, but physically the file is stored in the form of blocks. Okay, that's the overall concepts of distributed file system. And in Hadoop we use something called HDFS, Hadoop Distributed File System. Okay, so I hope everyone is clear as of now in terms of distributed file system, and I hope everyone understands this terminology. Is there anyone who doesn't understand this? Please let me know. So are we all clear as of now? Okay, Deepak has a question. Is there any relation between Spark, Hadoop and Hadoop 2? Okay, so Deepak, I'm sorry, one more thing. Rahul Ranjan has said is stuck. What is stuck, Rahul? I didn't get your point. Are you not able to see my screen? Okay. Okay. So looks like I'm getting some questions from the people in terms of how the copies is being shown to the user and how do we retrieve the data and all. So okay, yeah. So let me answer them one by one. First of all, yeah, Deepak has a question in relation between Spark, Hadoop, and Hadoop 2. So Deepak, we will get into the difference between them, but then at a high level, Hadoop is a framework which has three core components. Okay, which is a framework to support storage of big data as well as processing of the big data. So it has something called HDFS for storing big data. It's a storage layer. It has something called MapReduce for processing big data. And it has something called YARN, which is a cluster resource manager. All right. All these together forms entire Hadoop. Okay. This is about Hadoop. Now, in Hadoop 1.0, this is Hadoop basically 2.0, you can say. In Hadoop 1.0, you had just SDFS okay, and MapReduce. There was no yarn. This is Hadoop 1.0, this is 2.0. And in 1.0, in HDFS, as you can see from this architecture, there was only one name node. There was no backup of the master available. So if master goes down, it becomes single point of failure because I don't have any other node which remembers the metadata of how to retrieve the data from the cluster. Okay, so there is no backup, but in case of Hadoop 2.0, you have name node high availability in terms of HDFS. There are also some improvisation that is done on MapReduce framework compared to older MapReduce API, which is more user friendly for the developers. And then they introduce yarn, which is basically cluster resource manager, which segregates the responsibility of a job tracker, which was doing the resource management as well as application lifecycle management in Hadoop 1.0. But now in 2.0, the entire cluster resource management is outsourced to yarn. And MapReduce just does the functionality of executing jobs and managing the life cycle of entire, all this MapReduce and shuffle and sort for each MapReduce job. So basically, there are a lot of improvisation done on the framework itself, which makes it, Hadoop a more better and reliable framework. Now, on top of that, there is something called Spark. So the reason why they introduced Spark, because to process the data which is stored on HDFS, we just had one better technology which is called MapReduce initially. But MapReduce was not doing a good job in lot of use cases like iterative analytics, interactive analytics, and I'll be covering all of them step by step. This is just a first class. We'll definitely get into all of them in detail. But right now, just assume that there are various scenarios, which is interactive analytics, iterative analytics, where MapReduce was not performing well. It was very slow, and people wanted some framework which can actually do it much faster. So that's where the need arises for Spark. So I'll be presenting even white paper. I'll be sharing it with you, which has a lot of details about what was the motivation behind Spark. Okay, so Spark has been developed to replace MapReduce. In fact, a lot of people have a question: if Spark is there, what is the use of MapReduce? So just understand one thing. As a framework, yes, it can replace MapReduce. But MapReduce is more beyond framework. It is actually way of programming. It is a paradigm, which means you divide your data in map. You divide your logic, in fact, in map and reduce way, and then you process the data. So that thought process of solving a problem in the manner of divide and conquer, which is map and reduce, is not going away. It is still there with Spark. And Spark can write MapReduce programs. It's just that internally as a framework, it was doing map, shuffle, sort, reduce with a lot of IO calls, which is being eliminated by Spark, which we'll be learning, where it is doing all the stuff in memory. Okay, so Spark is definitely performing better as a framework compared to MapReduce in terms of processing the data, and it can give you faster results. That's why Spark has been introduced. Okay, so and one more reason to introduce yarn was earlier there was a tight coupling between MapReduce and HDFS. So if I want to process any data on HDFS, there was only one way, which is MapReduce. But now with the help of yarn, I can use Spark to process the data. I can use MapReduce to process data stored on HDFS. I can use any other program. For example, I can have, let's say, Storm, or I can have any other distributed processing framework which can process HDFS data via yarn. So it becomes more generic framework to process the data, right? So remember one thing: Spark is not a replacement of Hadoop. First thing, okay? So if you are thinking that it is going to replace Hadoop, that's a wrong assumption. Spark is designed to work with Hadoop. It may replace MapReduce. So when you are writing all your distributed processing logic, you may not use MapReduce framework, you may use Spark framework, because as a framework, it gives you faster performance in terms of processing the data. So yes, as a processing layer, Spark can replace MapReduce. But it is not going to replace Hadoop, because Hadoop has yarn, Hadoop has HDFS, which is storage and cluster resource manager. All right. So that's the difference. So is it getting clear, Deepak? Does that answer your question? I have just given you a high level overview. We definitely need to go through a lot more details to understand it, but just to give you an answer quickly, I just thought this is important. Okay, cool. Okay, I got couple of questions in between, so let me address them as well. Okay, I got questions from Omkar. Omkar, I'll come back to your question. I also got. Okay, so excuse me. All right. So by the way, first of all, how many of you have not attended, Hadoop training from me? I mean, just wanted to understand because some of the concepts of distributed architecture, HDFS architecture, I'm sure if someone has attended from me, he or she would have definitely gone through it. But if someone has not attended from me, probably they may not have gone through it because that is not. Maybe people don't cover it normally. Okay. Okay. So I got couple of people's response that they did not. Okay. So what I would do is, since a lot of people have some questions on some doubts on the SDFS part, is it okay if I just take few minutes to explain the SDFS architecture quickly? Okay, that is like a write flow, entire write architecture. Okay, sure. So I just want to get I mean acknowledgement from everyone because I just want to make sure that some people I'm sure have gone through it earlier. Okay, so looks like people are fine. So let me go through it. Let me explain that because it's very important to understand that. Yeah, sure. Let me just do that so that we all. Yeah, I just want to make sure that by the time we cover Spark Core, I want you to be very confident in understanding SDFS, entire the core of SDFS, the core of MapReduce, and the core of Spark. Once you complete that, trust me, you are good to go with any Spark setup. You don't really need to be waiting for all the Spark SQL and all that. That can be learned later, not a problem. All right, so we'll understand two important architectures, and then I'll show you some small demo of what does it look like when we store data in SDFS and where does it actually get stored. That way, we'll just make sure that our understanding is clear in terms of storing the data. So I'll just quickly go through it. So basically, when you write this command Hadoop fs -put, and you basically write source and destination. Okay, this is the command that you will write to execute to copy any data in SDFS. So what happens behind the scenes? Basically, there is a client who internally entire this command is basically being written into some programs, right? So entire Hadoop is written in Java. So there are some APIs which are being written to implement that entire command. So I'm just explaining that logic. So there is a client who actually talks to an object called distributed file system. That's a class, by the way. It's a Java program, and it actually makes a call to the name node. Okay, I'll just I'll avoid some of the high level overview APIs. We don't need to know about it right now. So it makes a call to name node, and it tells that there is a client who wants to write the file. Name node will do the validation on these two paths, source and destination location. It will check whether source path exists or not, whether destination path exists or not. So source will exist, fine. Then it will check destination. Now, what is a destination? It's a virtual path, right? You can just give any path. Let's say under user, under data, I want to store a file called f1, f1.txt. This is my SDFS path, which is, as we just discussed earlier, it's a virtual path. It's not a physical path. So name node will first check whether this path exists. If it is not, if it is exists, by the way, then you can't overwrite the file. I'm sure all of you know that SDFS will support warm, write once, read many times. You cannot rewrite the data, you cannot overwrite the data on the same location if it exists. So it throws the error. That means path should not be present. After that, name node checks the client's write permission, whether client has a write permission to write the data or not. Once these permissions are validated, then then name node basically gives the control back to DFS, saying that I'm good with it. You can go ahead and write the data. So distributed file system will actually create one more object called FS data output stream. Okay, which will be given to client. Now client will talk to this object to write the data further in the HDFS. Okay, so that's the first call. After that, what happens? Let me just draw some boxes so that we can understand it better. Right, so there is a client, as we know, he is going to talk to now FS data output stream object. It will create internally two components, acknowledgement queue and data queue, and there is something called data streamer. Okay, this is his name node, these are some data nodes. Alright, so what happens now is, let's assume there is a file which we want to write in the HDFS. So client will know this file is available in the source location. As you all know, this is the source location where the file is available. Let's assume its size is 128 MB and the default size of every block is 64 MB in HDFS. So what happens, the FS data output stream will actually divide your file in multiple small packets. Okay, and how does it divide that? There is a property which is being used in one of the configuration property, which is HDFS site.xml, where the property name is DFS dot packet dot write is 8 MB. By default size is 8 MB, but you can change it. So this property is used by FS data output stream to divide your file into 8 MB packets, and then suppose if you want to write 64 MB blocks, right? How many packets we need? We need approximately 8 packets, right? First 8 packets will make up 8 into 8 is 64 MB. So these 8 packets are being loaded into the data queue like this: P1, P2, P3, P4, as you can see, right? And so on and so forth. So like that, all the packets, all first 8 packets are loaded here in the data queue in memory, and then it will start one thread, which is a data streamer. So what it does, it will go and pick up first packet from the data queue, and then this thread is going to write the data in the HDFS. When we say HDFS, it is nothing but name node and data node, right? So it has to write the data, and always we know that the data gets written in data nodes, not on name node. Name node just remembers metadata. So data streamer will have to first contact name node. By the way, by that time it would put first this packet in the acknowledgement queue and then contact name node. Name node will give him the information that these are the locations where you should be able to write the data, like data node 1, 3 and 5. Out of, let's say, 10 data nodes, we are assuming that there are 10 data nodes in the cluster. So name node gives him 3 data nodes. Along with that, it also gives him one block ID, which is, let's say, block 001. Okay, this is the block ID. I'll tell you what is a block ID. And parallelly, name node updates its metadata. That's okay. This is the no, Ganesh. There is no job tracker involved here. It's all between name node and data node. Job tracker gets involved only in the MapReduce operation. Okay. This block 001, and it will also remember that this block is going to be stored in data node 1, 3 and 5. So as I said, Ganesh, this entire stuff is being happening once you execute this command. As a user, when we write or execute this command, behind the scenes, everything is going to be started. This command is internally being written as a Java program, right? In Hadoop framework. When you install Hadoop, all these libraries are being used. When you execute this command, it will actually use this code to basically do this operation which I'm explaining you here. Okay, there are some commands. So you just go and open the source code of distributed file system, and from there you will get the details about how it calls different methods and how it is happening. Okay. Yes, Satya, that's right. So here I have given 3 data nodes because we are assuming that the replication factor is 3. I'm sure all of you know that Hadoop, when you store data, the default replication factor is 3. Alright. So that's why we are assuming that name node has given 3 data nodes. And now once it knows this information, the data streamer will start writing these packets in these 3 data nodes, one by one. So it will write, let's say under block 001, it will create a file. By the way, it is going to create a file in the local file system of this machine. Okay, data node 1 machine, and that file name is 001, which is a block ID. So every block is having a unique name, which is nothing but a block ID. The block itself is also a file only, right? So that file have to be stored with some name, that is a block ID, which is given by name node. And in that it will write this packet P1. After that it gives a control to data node 3 where it writes packet P1 and so forth. Similarly, data node 5 will also write a packet P1 here. It will respond back to data node 3, then data node 1. Once the acknowledgement comes, it will respond back to the data streamer. So that's how one packet is successfully written. Once one packet is written successfully in all the 3 machines, data streamer will remove that from the acknowledgement queue, and then it will go to the next available packet from the data queue and start writing the data into the data nodes. Now for the next packet, it doesn't need to go to the name node because it already has all the details like what all data nodes I should write. Why? Because it can write all 8 packets in the same block. It doesn't need to know more information, right? Because it already know that. So it can directly append these packets into the same block file, and likewise it completes all the packets writing, right? So that's how basically the packets writing are being done like this, okay, in the data nodes. And here all these packets will be removed like this. So that's how one block can get written successfully in all the 3 data nodes. Okay, I have just gone through a little high level, because in the interest of time, but I am sure all of you can understand this, like how the data gets written. So this is how one block gets written successfully into the HDFS, into the data node. Once the block gets written successfully, data streamer gives the acknowledgement to name node saying that this block is completed. After that, we also want to know like what happens to the second block, right? So I'll also explain that the second block is written parallelly, by the way. So you can just say that this is how it will create, like say, data queue, acknowledgement queue, and data streamer 2. Okay, and it will basically load these packets parallelly into this queue. So all the second block packets are loaded in the another data queue, and then this guy is going to start writing these packets by contacting name node and getting that information from him, and then he may write it into the another available data nodes. So basically what I'm trying to showcase, highlight a point is this second block can also be written parallelly, just as the same as we understand for the first block, right? Which means block writing is parallel. In a file, 2 blocks can be written parallelly because it creates 2 threads to parallelly write those data in data nodes. But packets within the block is sequential. Okay, so there is a thread pool available, and based on that it creates number of parallel blocks. it can't, let's say if there are 100 blocks, it can't create 100 threads. So there is a thread pool size which you need to configure in one of the configuration file, and accordingly it will actually basically create that many threads, that many blocks can be written parallelly. All right. So this is how we complete writing one block. There are some failure scenario also which we need to understand. But before that, I just want to make sure that everyone understands how the packet, how the block is getting written. So is that clear with everyone? Okay, so Rajesh, to divide the block into multiple blocks, there is no logical approach. Why? Because it just goes by the size. And I see your point. It's a valid point that if a file with, let's say, some word is split into two blocks, then how does it handle? So that's where there is something called block meta file which is available with respect to every block, and it actually uses that information which is being stored in some other block, so that while processing it will retrieve that leftover part to this block. Okay, so that will be done by job tracker. And that is being taken care by Hadoop framework itself. Even if the data is partially divided, Hadoop framework will know where the other part of the data stored in which block. So while processing that block, it will get that remaining portion of that data from the other block and give it to the same task so that it can process in a combined manner. Does that answer your question, Rajesh? Yes, definitely. Hadoop framework needs to understand the different types. So when I say different types, you will have different input format classes available, which will basically understand what is the type of your data. If it is a binary data, you have sequence input file, you have text input file format, you have multi-input formats. There are different XML input format class, JSON formats, Avro, Parquet, lot of formats are available. So there are different input formats available, which helps you helps Hadoop understands how to process the data. So some of the input formats are already available as part of Hadoop APIs. If let's say you are writing your own format, then you can also you can override input format class, you can create your own custom input format class and let Hadoop know that please use this input format to understand this data, right? So you can do that as well. But yes, Hadoop needs to know all the input format class so that it can understand what is an input data. Yes, anybody has any further questions in this concept? All right, cool. So let me move forward. Okay. Now I'll just cover some of the failure scenario as well, just to make sure that everyone is on the same page. By the way, here, if you can see, if I can explain you here, let's assume that only 3 packets are written successfully. We are in the right flow, okay? We are writing the packets and we have not written all these packets. They are still there. Only 3 packets are being written. And then data streamer goes and writes 4 packets. And I just want to explain also what happens in case of failure. So it writes packet P4 and then it goes to the data node, next data node in the pipeline. When it is, let's say, trying to write some data of this packet, let's say something goes wrong and this machine fails. When that happens, data node 3 cannot send acknowledgement back to data node 1 and it cannot send request to data node 5, right? So when this happens, what does it do is basically it will not be able to respond to data node 1, and at the same time data node 1 can wait only for the timeout period. Till then, if it doesn't get any response from data node 3, it will send an acknowledgement back to data streamer saying that data node 3 fails and packet writing P4 is failed. When that happens, data streamer which has loaded this packet P4 in acknowledgement queue, it moves back that packet on the top of the data queue, and at the same time it goes and informs name node saying that there is something wrong with block writing. Block 001 is failed. So what name node does, it will immediately remove all this information from this block. It will remove block 001 to block 002. It will basically remove all the old information of block 001. Okay. Now this is the new information. It gives you the new block ID. New block ID has been given by name node to the data streamer, and it will tell that, okay, why can't you start rewriting it in the new block ID? I'll answer the question on why new block ID is needed, but data streamer, once it gets the new block ID, what it does, it again rewrites that packet P4 into data node 1, where it has already written packet P4, right, in the file name with 001. So now it renamed this file with 002. Okay, and then data node 1 will send a signal directly to the next available data node. So by the way, I have not explained all this, but then during the failure it will update this pipeline, it will remove the failure node, and it will update that now this guy points to the next available data node. So all these things are done. So data node 1 will talk to the next available data node and then tell him to do the same thing, rename the file with 002, block ID 002, and write packet P4. Once that is done, it will send an acknowledgement back to data node 1, and once it completes, data node 1 sends acknowledgement to data streamer, and that's how packet P4 is written successfully. Post which all the other subsequent packets will be written in that fashion. So now you will have P5, P6, P7, P8 are written here, same way P5, P6, P7, P8. Okay, so basically all these packets are written successfully in two blocks, data node 1 and data node 5. In these two data nodes, these packets are written completely. So block 002 is written completely in two different data nodes. That's how the entire write completes. Now do you see any problems here? We know that we need to explain why new block ID is needed, but apart from that, do you see any other problem here? Yes, that's right, Dipto. So replication factor is, yes, Satya, that's correct. Replication factor is not achieved, right? We have 3 as a replication factor, but we were able to write only 2 copies of block 2. By the way, Rajesh, there is no duplication of the data, right? We wanted to replicate the data. There is always a replication that happens on every block in HDFS. So when you store a file in HDFS, oh, okay, fine. Then it's good. So yeah, so the replication is not achieved here, and we were able to write only 2 copies. So how does it normalize? So it has to normalize it by adding an extra copy. So what it does, it uses a process HDFS balancer. Okay. It basically does this job of what. So HDFS balancer, by the way, is a daemon process which is running in name node separately, and that process will actually make sure, I mean, it will periodically, checking all the metadata information of the name node and find out which block is having the total copies less than 3, less than the replication factor. Those blocks are considered as under replicated block, and it will go and create, if it finds out that yes, block 002 is actually under replicated, it goes and creates extra copy in any of the available data node which is suggested by name node. So name node tells him that okay, you go ahead and create this extra copy in one of the other available data node. So it just goes and creates that extra copy there. So that's how replication is normalized. Okay, That's what happens, but that is not part of this write architecture. It is a separate process which is being achieved by HDFS balancer. Now the same way, that's about one point. Now another point is we wanted to understand why new block ID. So let's assume that we did not get this new block ID and we were having only old block ID. That means I'll just use this old block ID here. That is data node 3. There is data node 3 here, and these are all old block ID only. Now in this case, you can see here that if we don't get new block ID, what happens? Ultimately, after entire write is completed, you have block 001 with complete data in two machines, data node 1 and data node 5. But data node 3, which was failed, had just partial data in block 001. Now after some time, let's say this machine comes back and it starts sending heartbeat signal to name node, which means it says a name node that I'm alive in the cluster. After that, let's say once your write is completed, there is a client who wants to read this file. He will go and check with name node that I want to read this file. So client will tell him that, okay, you go ahead and read the data from this machine. Now when client will check whenever client wants to read the data, it has to go to the name node to read the data. So when client talks to the name node will tell him that, okay, you go ahead and read the data from any of these three machines. Why? Because name node has this metadata information, right? So it can ask client to directly go and read the data from data node 3, because name node doesn't know which block is complete, which block is partial. So in this case, what happens? Client will get to read partial block of 001, partial data of block 001, right? So this is the problem, and to avoid this problem, name node will give you new block ID, so that even in case of failure and after that if data node 3 comes back again, name node will never know any information about data node 3 or block 001. So if client asks name node to read the data, name node will never ask client to go to the data node 3 and read that data for that file, because name node doesn't have that information in the metadata. So to safeguard client from reading partial data, it actually gives you the new block ID. Okay. And apart from that, one more point, which is what happens to this partial block. So when the client receives the heartbeat signal from data node 3, which is failed, right now it has now started again, right? So what name node tells, by the way, I hope all of you know that every 10th heartbeat, each data node will send a block report. And in the block report, it tells that these are the list of blocks I have. So when data node 3 sends that block report to name node will check that you are saying that you have block 001 with me, but I don't have any such information about block 001 in this metadata, which means you are holding a corrupt block or an orphan block. These blocks are referred as an orphan block, and it again asks balancer to go and physically remove this block from the data node 3 machine. That's how it cleans up all the partial or corrupted data as well. So this is how entire data management happens, data storage happens in the HDFS. Okay, I explained you little high level, but in the actual training, I'm sure people know that we do go into much more detail. But that's how basically overall it happens. So I'm sure you got a fair idea about how data gets written and what happens in case of failure. So is everyone clear as of now? Any questions anybody has on the data storage part? Specifically, I request from the people who have not attended my classes of Hadoop. So just wanted to know if they are fine with this, if they are clear on this. Okay, good. So looks like everyone is clear. So let me go ahead and show you one simple demo of understanding what we have learned so far. By the way, I'll be sharing a guide. I'm sure some people already have this who have attended this course from me. But yeah, I'll be sharing a guide on how to install Spark in your machines. We'll talk about installation later. So this is the Cloudera cluster. So I'll be using a Cloudera cluster. It's a Cloudera distributions of Hadoop, which we'll be using to do all the practicals. So when you install that, you get all the components ready-made installs and configured. So we don't need to worry about installing them separately. Even Spark is installed here. Okay, so we'll be using Spark as well from here as well. So I'll just show one simple demo on how we can store data in HDFS and what happens behind the scenes, like where the blocks get created, just to validate the theory that we have learned so far. Okay, so this is my home directory. I'll be creating one file. I'll be creating a test file. Okay. I'm just writing some message, sorry. Okay, this is my file with one line which I have created in the local file system. So if I do this, you will see test.txt created here. Okay. Now I want to copy it in the HDFS. I'm sure all of you know how to access HDFS and all that. There is a UI version of HDFS which is available, so we can directly go to this tab Hadoop. Under Hadoop name node, there is a tab available called Utilities section. If you click on this utility section, browse the file system, you will actually get to see all the files and folders created in HDFS. Okay, this is about accessing it through UI, but you can also access it through the command interface. So I can write this Hadoop. I'm sure all of you know this Hadoop fs-ls root, which gives you the list of files and folders in the root directory of HDFS, right? So you can see all this here under root. You can see all the files and folders of your HDFS. Same way, you can see all of them here as well. All right, cool. Now let's create one directory here. Anyway, we are going to do a lot more. We will basically use our HDFS a lot more in Spark as well. So we will be creating files here and loading files, creating directories. So I'm just creating one directory, let's say Jamin under root directory. So it says it's created. You can just check here itself. Jamin directory is created, which is empty right now. So I'll be copying that file here. Hadoop fs-put test.txt under Jamin directory in HDFS. This is my local file system path. This is my HDFS path. I want to copy data into HDFS. So I'm basically following that right architecture that we have learned so far. Okay. Behind the scenes, this right architecture is being performed to write this data. That means this file is being divided into multiple blocks and it will be stored in multiple machines. So if you see this, the test.txt file is copied here, and if you click on that, it will basically have a lot of details. So I'll explain all of them, but right now this is how virtually you can see this. This is a virtual path. Okay, this is not a physical path. How do you prove this is not a physical path? See, under root there is a Jamin directory. So if I want to go to the physical file system, I'll just say cd root. This is my physical file system. If I do ll, I can see all the files and folders under this directory. Do you see any folder or directory which says Jamin? No, right? That means it is a virtual directory. It is not a physical file system. Right? That is one way of proving it. Now you already copied the file. So the question comes is where the data gets stored physically. So if you click on this file, it says Lot of information about that file. By the way, this is a Cloudera's utility that through UI also you can get all these details. If you don't know all this, you can use this command. I'm sure you would have learned in your Hadoop class. Hadoop fsck is a command. Then give the file name -files -locations -blocks. You can say HDFS also instead of Hadoop fsck. Once you do that, it actually shows you the locations of the blocks which are mentioned here. So this is the block ID, okay, and it says it is stored in this machine. So the same thing will be printed here also, with all the details about the replication factor and everything. So you can get details about how the file is being divided in which block. As you can see here, you can get to see this block ID, and then there is I think, yeah, this is the machine where that block is stored. You can check the replication factor, which is 1 here, okay. Then yeah, that's it. So total replication factor is 1, and the block is also replicated as 1. So there is no under replicated blocks. So these are all details you can get for a particular file through command line itself, or through UI also you can get to see this, okay. Now the question comes is where this block is stored. We got to know that yes, this file is divided into physical block, but where this block will be available, where can you go and find it? So as we know from the architecture that the block normally gets stored in the data nodes, right? As we know, these are the block IDs, which means nothing but this. This is also a block ID. So the block will be stored with the file name, which is this block ID, and it will be stored in one of the data node machine. In our case, it's a single node cluster. So obviously data node will be running in the same machine where name node runs, right? So let us go and find it out where the blocks are stored. How do you know where the blocks will be stored? How do you check the path? So for any Hadoop clusters, I'm sure that also would have been covered, but just to get you an idea that you just type which Hadoop, which will take you to the path. I'll directly go to that location, user lib. So any Hadoop cluster, this is how you find out where Hadoop libraries or Hadoop configuration files are installed, okay. And under that you will see some properties. You just need to go to HDFS site.xml. You can see a lot of information about block size, the replication factor, all of them. But the most important part is this, which is dfs.namenode.name.dir and datanode.data.dir. So this is the location where blocks are being stored by the data nodes. And this is the location where name node stores fs image and edit files, right? Fs image and edit files are, I'm sure you would have learned the checkpointing process. So these are the files which contains your metadata and the backup of all your metadata information. So name node stores all the metadata information from memory into the physical file system. Just let me show it here. This is how it does it. Let me just put here. So basically, if this is your name node, okay, it will have a RAM. Okay, this is a RAM in this machine where it stores all the metadata, right? Metadata of your cluster. These metadata are stored in the memory, but it has to take a backup also somewhere. So it keeps dumping all this metadata in the local file system of the same machine where name node is running under the file called fsimage and edits file. Okay, so these are the two files which will basically store all the metadata information. Now what goes in fsimage edits, these are like the detailed concepts, but right now just assume that all the metadata will be stored here. And the data nodes which are available in the physical, in the cluster itself, if this is your cluster, then data node will store the blocks. So for example, if you have a file which is divided in two blocks, block A and B, so that A will be stored in the local file system here, B will be stored here. So what is that path? That path is this datanode.dir. So every data node will have this physical path in their local file system where they store data blocks, and every name node will have this path where they store fs image and edit files. Okay, so I'll copy this path and I'll go under this directory to check that block information. So let me open another terminal. I am inside this. I'll go to HDFS. DFS. There are data name nodes. So data node stores here, name node stores all the metadata here. So we'll go inside data. It says permission denied, so you need to log in as a root user. Now we'll go inside data. There is a current folder. So I'll go inside some of the directories. Okay, then I'll explain what I'm doing here. So this is a default path, and any Hadoop cluster, which is a distribution version of Cloudera, Hortonworks, or MapR, any Hadoop, and by the way, if you go and work on any companies, you will definitely get to work on only the distributions of Hadoop. You don't really get to work on Apache Hadoop. Nobody uses that. Only distributions are used because they are more stable and they have a lot more features and a lot more integration points. So everywhere this path is common. Till this portion, it will be dependent on your cluster Hadoop admin. He will decide where this will be stored. But after that, all these are common to every distribution. So I'm just showing you the way to understand where the blocks are stored, and where you can see all the configuration files. So any Hadoop cluster, these are the steps you need to follow. So I mean, and these are default directories which are being created. There is a block pool which is being created. There is a separate concept of block pool which I don't want to explain it right now. But assume that the data will be stored here. So inside this, it creates multiple directories. So let me go to one of the directories. And if you do this, you will get to see all the blocks inside this. These are all physical blocks of the file which you have stored in HDFS. Why there are already some blocks are created? Because there are some data in the Cloudera Hadoop admin, Cloudera clusters basically. Some data is already created by the Cloudera because they are using Sbase and they are using Hive and all that. So some data is already created. That's why you have a lot of other blocks. Even I have created some data. That's why you can see a lot of blocks here. Now, our question was where this block will be stored. So we just got to know that this is the location it should be stored. So let us cross verify it. We will go to this file and open it and see whether the data is there or not. So the last 4 digits is 2213. So I'll be searching that block. It's here only. Okay, BLK, last 4 digit is this. So I'll just do VI and open that file. As you can see, we have seen the same data which we have stored in the test.txt file. Hi all, welcome to the Spark. So that's where your physical data gets stored in this block. Okay. And virtually you can access it in this path /j/test.txt. When you access this, what happens behind the scenes? It will go to this block only, okay, and read that data from this block and give you that data, right? So this is the difference of virtual file system and physical file system, like how your data gets physically stored. So is everyone clear with this concept? Any questions anybody has? All right. So let's move forward. So that's about HDFS and distributed file system that I just wanted to cover. So we are now clear with basic concepts of what is distributed file system and how do we store data in distributed file system in the form of HDFS, because that is what we are going to use for this training as a data storage layer, right? And now we want to understand more about MapReduce first, and then we'll go to the Spark. Now, before I get into the MapReduce, I want to cover this point, which I think someone has asked earlier, which is like what exactly, how do you look at Hadoop for ecosystem versus Spark ecosystem, and where do they fit in? So I just want to clear that doubt first. So let me draw some boxes and I'll just understand this. Don't worry, I have drawn a lot of boxes, but we'll understand them. So that's fine. All right, so let me just quickly write them. So I just wanted to understand the holistic view of entire, how Spark and Hadoop fit together and what are the differences between other components. So this is your HDFS. This is Yarn. Okay. This is MapReduce. So these three components together we know becomes Hadoop, right? So when you install Hadoop, you get these three components, not anything else. Other stuff are something which you need to configure it by yourself. So you have Spark. Okay. Same way you have other frameworks like Storm. There is, some components like Scoop and Flume to load the data into HDFS. These days now a lot of other components have come up, so I'll just write it this way. A lot of distributed processing frameworks are there. You have Hive, Pig, Mahout, Spark SQL, Spark MLlib, Spark Streaming, and GraphX. And this is Uzi. Okay. So Solar is a search engine, Ganesh. So Apache, Solar, Lucene, all them like are search engine which basically starts. We can be fit into HDFS, but they are not really a good use case for HDFS. Okay, yeah. So let me explain them. So basically, see, there is a layer which comprises of Scoop, Flume component, which are nothing but which are the components which helps you to bring the data into HDFS. Okay, they are called data collection layer, which loads the data into HDFS. HDFS being the storage layer. Now earlier we know that MapReduce was having a tight integration with HDFS. So if any logic you want to write to process the data or to analyze the data on HDFS, you have to go via MapReduce. There was no other alternative route, right? So that was a tight coupling between MapReduce and HDFS. So what they have done in Hadoop 2.0, they introduced one more layer called YARN, which is also referred as Cluster Resource Manager. Okay, it is actually used for executing any processing logic using any processing framework, not only via MapReduce. So first they made it more generic so that other processing framework can also use HDFS to process your data. So that was one objective. Another objective was better cluster resource management, where they split the job tracker functionality into multiple tasks, and then they kind of use their own processes to do it in a better way. So there is a YARN architecture which talks about that. So overall, it does cluster resource management, and it makes it more generic so that any processing framework can execute it on the HDFS data. So of course, MapReduce was processing data on HDFS. Spark can now process data stored on HDFS directly. You can use Storm also, which is more a real-time analytics framework, which can also process data on HDFS rather than using Spark. And likewise, there are many other distributed processing framework you can use, but currently this is a more like predominant in this space because of the advantage it provides with a lot of other ecosystem components and its framework. So yeah, if I'm using MapReduce, then I have to write all the programs in MapReduce using Java. So what they have done, they abstracted that using Hive and Pig. So just to kind of write, instead of writing entire program in Java in MapReduce, you can use SQL. So this is again an SQL version of MapReduce, where you write all the SQL queries using Hive, which can be internally converted into MapReduce program to process data stored on HDFS. Same way, Pig can be used to, if you write all the analysis logic in Pig script, it can be converted into MapReduce to store data to process data stored on HDFS. So Hive and Pig are basically an abstraction layer on top of MapReduce. It is for the developers who want to write analysis logic in a language other than Java, and basically mostly like SQL or Pig Latin scripts. Okay, they have their own advantage. You can write the code faster, but of course they have their limitations also. You don't get the complete control like you have it in Java in terms of development. So they have functionalities like UDF, user-defined functions. You can do that as well to write your logic and integrate it with your Hive query or Pig scripts. So that's about Hive and Pig. You can also use some machine learning libraries in Mahout. Mahout will basically is a component which will have all the machine learning algorithms written in the form of MapReduce, which are going to be executed on HDFS. Okay, so these are the three components overview which can basically help you to process data stored on HDFS via MapReduce. So they all use MapReduce framework, by the way. Same way, if you don't want to use MapReduce, you can use Spark. So Spark core, you can write your program in three languages: Java, Scala, or Python. These three languages are supported in Spark. Entire Spark, by the way, is written in language called Scala, which we are going to learn in the coming sessions. But yeah, you can write this program in either of this language. But there is also an abstraction layer, like Spark SQL is one component where you can write SQL and which will use internally Spark core engine to process the data stored on HDFS. You can also use Spark MLlib, which is equivalent to Mahout. So instead of using Mahout, has all the machine learning algorithms written in MapReduce way. MLlib will have all the machine learning algorithms written in Spark using Spark core. So it uses Spark core framework to process data on HDFS for a better performance. Then there are extra components. So compared to MapReduce, Spark will have something called streaming, which is the important advantage that Spark gets over MapReduce. MapReduce is just a batch processing framework. It cannot process real-time data. Why? We are going to learn that when we talk about MapReduce Spark. But right now, assume that MapReduce does batch processing or historical data processing. It can't do real-time processing. In Spark, it can do both, batch as well as real time, and real time can be achieved using Spark streaming. So we are anyway going to learn in detail about what is Spark streaming, but that's how it actually helps us to process the data in real time. And then there is something called GraphX. which is basically used, which has a lot of APIs again written in using Spark core, which helps you to develop graph. It has a lot of graph algorithms which basically helps you to do a lot of analysis using using Spark core engine. So you can develop a lot of graphs, solve some graph problems like distance between two nodes, which is the shortest node. Shortest path algorithm can be written in a distributed manner using GraphX APIs. So a lot more stuff you can achieve using GraphX, and I'll be showing you one demo on GraphX as well when we come to that session, which will be the last session, by the way, for our training. Okay, so these are different components. By the way, Pig is going to be supported in Spark in the recent releases of Spark. They are going to have a support for Pig as well. So you can write Pig scripts. You don't need to change anything. There are some minor configuration changes, and automatically you can switch the processing engine. Instead of MapReduce, you can directly use Spark to process the data. Same thing is happening for Hive also. If you want to execute Hive queries but not convert it into MapReduce and directly convert it into Spark, that is possible using Spark SQL. So there is something called Hive context which is available in Spark, through which you can do it. And I'll be showing you all this using demo so that we'll understand it better. Right? So these are basically different ecosystem components and how different components fit together. And of course, Oozie is a workflow and scheduler management system which actually schedules the entire workflow, and it triggers the jobs in a step-by-step manner, right? So let's say if you have a requirement where you want to get the data from a database into Hadoop cluster. So you want to import all the data into Hadoop cluster, and then you want to basically process them. So first step is importing it. You can use Scoop component. I don't want to explain Scoop and Flume because I'm sure you know about it. So Scoop will help you to import structured data from RDBMS into Hadoop. And then let's say you want to write MapReduce or Spark program to process that data. Okay, and then you might want to use some report generation APIs to basically generate the report. So if you want to achieve all of them, you can basically, you want to, let's say, complete this functionality. So these three steps have to be executed in sequence. Step 1, then step 2, and then step 3, right? So what are we doing? We are creating one workflow. This is called one workflow, and we are creating it using Oozie. Oozie will help you to create that. It has 2 XML files. I'm sure you have gone through Oozie as well, so I don't need to go through the details. But it has, excuse me, it has a file called workflow XML, which helps you to create workflow, and you can automate it by scheduling it. You can actually schedule it at every regular interval times. So it has a scheduler also, right, which makes your life easy. Once you write those programs, you can do it. You can execute them on a repeated manner on a different data sets and generate variety of reports, do variety of analytics on a daily basis. That's what a lot of company does. So Oozie is a wonderful workflow scheduler framework available, which can schedule all of them, which is written here. All right, so this is how an entire big data stack you can see. There are other components like NoSQL which can fit here. NoSQL databases, like you have HBase, Cassandra, MongoDB, which can directly talk to the HDFS, and you can make Spark talk to the NoSQL and process data stored on NoSQL. That is also possible. Okay, of course via YARN. So you can decide to store your data on NoSQL database in let's say HBase or Cassandra, which internally stores in HDFS only. But these database will provide a lot of advantages over HDFS. For example, dynamic schema creation or in-place update. As we know, in HDFS we can't update the data, but in NoSQL database, when you create table, you can update the data as well. You can append the data as well. And there are concepts like indexes. You can create indexes on the HBase table so that your query retrieval will be faster. We can't do it on HDFS. We have other means to do it, but in HDFS it's a flat file system, so it doesn't support all this. Okay, Sanjay has a question. If you use Spark, is there a need of MapReduce, or we can manage with Spark over MapReduce? So Sanjay, you don't really need to use Spark over MapReduce, right? There is no need of that. Yes, your question is valid. I can directly completely remove this component by just using Spark. That is possible. However, I told you one thing, which is MapReduce is actually not just a framework. It's a way of programming, way of distributed programming, which is using map and reduce paradigm, right? Divide and conquer. So that paradigm is still used in Spark, which means you can still write MapReduce programs using Spark APIs, but it uses internally Spark engine to process the data, right? So I will show you some examples which uses MapReduce programs in Spark as well. So Spark, yes, definitely as a framework, it can replace MapReduce, but MapReduce paradigm is still being used in Spark. Does that answer your question, Sanjay? Okay. And yes, Omkar has a valid point that Spark does not work on Hadoop 1.x. That's true, actually. It's older version of Hadoop. Anyway, Omkar, by the way, nobody uses Hadoop 1.0. Even the companies who are using it are trying to migrate it to Hadoop 2.0. Hadoop 1.0 is like a mess. It doesn't. You should not use that. It has a lot of flaws and a lot of problems. So Hadoop 2.0 has solved all these problems. So you should just use that. Okay. So till now I have just given you the the conceptual overview of different topics, different concepts, just to make sure that you understand. So we covered HDFS in detail by understanding how the data gets stored. We covered overall big data stack, where Spark fits, where Hadoop fits, and where Yarn fits, and all that. Now we are going slowly towards Spark. So for that, its rivalry is MapReduce. So let's understand a little bit on MapReduce first. We'll be understanding MapReduce architecture, and that's where I'm going to make you realize some of the flaws in MapReduce. It's not actually a flaw, it's a way the framework is designed, but we want to understand what are the challenges there, so that when I'm going to explain you Spark, it becomes very easy for you to relate that. So that's why I want to cover MapReduce architecture as well, so that it becomes easy for you to understand Spark. Okay. So till now, anybody has any questions? Yes, okay. I think Satya has a request. Earlier, I guess it also has the same request. So, by the way, everyone, please post your questions to all the participants so that other people can also see that question, and they basically get an understanding about what you are trying to ask. So, in case if you are comfortable, please do it that way. If you really think that I don't want to post it to everyone and you just want to ask privately, it's also fine. So I leave it to everyone, but try to make it to all participants so that everyone gets benefited with that question. Okay. So as of now, anybody has any questions? Everybody is clear so far? Can you please let me know that? Okay. So I got most of the response, but the people who have not responded, I'm assuming that they are fine, they are clear. Just wanted to make sure if you have any questions, please don't keep it as a doubt, because it is going to hurt you later point of time. So just ask, even if it is a basic question, please ask. I want to make sure that everyone is clear with this basic fundamentals, right? So that when we get into the the next level, advanced level, it becomes easy for you to relate all this. That's the reason why I'm taking time. So I always do that in the first session. I want to keep revising some of the concepts just to make sure people are on the same page, so it becomes easy for you to understand the advanced concepts. Yeah, sure, Dipto. So I'm going to come to that only. So by the way, yes, in case if you don't have questions, let's do one thing. So since this is a 4-hour session, we are going to take a break, and we'll be taking one break only. I don't want to take like multiple breaks. So what we'll do is we'll take half an hour break now. We'll come back after half an hour and we'll continue that. Okay? Is that fine with everyone? All right, sure. So cool, everyone. See you after half an hour. Hello everyone. Sorry for this delay. Let's get started. So I'll be now talking about the MapReduce problems, like what kind of challenges that a MapReduce have, limitations of MapReduce, and for that let us understand quickly the architecture of MapReduce. So by the way, just one thing I wanted to mention to everyone, that today we are trying to cover a little bit background on the MapReduce front and the HDFS front, so that when we get into the Spark tomorrow, it becomes easy for us to understand the difference. I'll be also covering the installation of Spark today, so that it becomes easy for you to understand how to install a Spark cluster. Okay, yeah, so we'll go into the MapReduce, and as we all know, right, MapReduce has three phases: map, shuffle, sort, and reduce. We basically want to let's say process data stored on HDFS. So we will start writing a MapReduce program, and then when we execute it, it goes through different phases of map, shuffle, sort, and reduce. So here, one second. Okay, let me first explain you what happens behind the scenes. So you have, let's say, you will execute a MapReduce code using this command, right? Hadoop jar. Then you have jar path. And then you have input and output path. Okay, so Hadoop jar path, then input and output path. This is the command you are going to use to process the data stored on HDFS, right? So let's assume that there is a file which you have stored in HDFS, which is having 128 MB size, so which has basically two blocks, block 1 and 2. So it is basically stored in two blocks, and this file which is stored in two blocks, there is an input path that you need to give, which is this file, okay, which is stored in HDFS, and then the output path is something where you want to store the output, and the jar file is something where you are creating a MapReduce program, and then you create a jar out of it and then process this HDFS data. So we are assuming that we have created a MapReduce program in Java, and then we are basically going to process that data which is stored here and generate the output. So when we execute this command, what happens behind the scenes? How does it actually work? So that's the architecture we'll be discussing quickly. So, and that's where I'm going to explain you some of the limitations of MapReduce as well. So this is my job client, which pass the control to the job tracker. So job tracker is a process which is, I'm sure all of you know what is a job tracker. It runs on a master machine, which takes care of executing a MapReduce. And when you execute this command, behind the scenes, the client will first get executed, and it will take this command, and then it sends the control to the job tracker. Now, once the job tracker receives its commands, it basically asks job tracker to give the job ID. So job tracker will give him the job ID. Let's say some J1 as a job ID. And after that, job client also validates whether input path exists or output path exists in HDFS or not. Right? Input path should be exist in the HDFS, because if you don't have data, you can't process the data. So it should be present. output path should not be present. Otherwise, it cannot overwrite the file in HDFS. So it throws error if it present. So these validations are done. It also checks whether client has a right permission. Everything is done. After that, it actually stores all this information in a HDFS shared location. In some default directory, it creates a directory with the name as job ID, under which it copies this file, jar file, input path and output path, everything. So basically, job client will now, once it does the basic validation, its job is done. Now it needs to submit it to the job tracker. But before it submits, either one way it can pass all the files over a network to the job tracker, but that will consume some resources on network. So instead of that, it puts it in the shared location, which can be accessed by all the other Hadoop processes. So HDFS is a shared location where it creates a directory called J1, which is the same job ID which is retrieved by the job tracker, and it copies all the files under that. By the way, every MapReduce program which is being executed on Hadoop cluster is referred as a job. And every job will have a unique job ID. So job tracker will give him the job ID, and then job client will submit that job. After that, it will submit the job to the job tracker. It will call a submit method. Once it submits the job to job tracker, your job submission phase completes. After that, job tracker will get these jobs in a separate job queue, where all the jobs will be mentioned here. Okay. J1, J2, J3, J4, whatever. So let's say all the jobs are mentioned here in this queue. Your job J1, which is, let's say, first job in the job queue. So by the way, every job will be first put it in the job queue, and based on the resource availability of the cluster, job tracker will pick up that job from the job queue and execute it. So this is a job initialization phase where there is a scheduler available in job tracker which is called FIFO scheduler, which picks up the job from the job queue based on first in first out order. Whichever job comes first, it picks up that job first in the job queue and then start executing it. So let's say J1, which is what we are going to execute, is the first job. So it picks up that. And now see, this is just a string. Job ID is just a string, right? So we need to know what is the source code, what is the jar file for this job, and what source code needs to be executed. So job tracker will take this job ID and again go to this shared location, read the data, and it tries to find out the directory with the same job ID name, and then reads all this information that this is the jar file, this is the input output path which I need to execute. Once it knows all this information, job tracker will create a multiple block. So job tracker will basically take this input file and it tries to, now it knows, right, that this is the input file which is available, which is stored in this location in HDFS. But it doesn't know how many blocks are there for this file and which block are stored in which location. So let's say there are, let's say this is task tracker 1, data node 1 machine. So as you know, right, that every slave machines will have task tracker and data node installed. Okay. So each machine will have task tracker and data node installed. Now what happens is, we are just assuming that let's say block 1 is stored here, block 2 is stored here, and they may be replicated somewhere here like this. Okay, it could be in this fashion, or let it be this way. It's fine. So three is the replication factor, right? So they may be replicated in this manner. But job tracker needs to know, right, that how many blocks are there for this file so that it can process that data. So how does, by the way, job tracker know this? Anybody has an answer? How does job tracker know how many blocks are there for this file? It just knows the input path of the file. If it needs to get the information about the blocks and the locations, how does it get that? Yes, that's perfect. So it has to ask name node to get the information. Name node will give him that information because name node is the one who has all the metadata information. So it checks with name node, gets the information, and then once it knows that there are two blocks for this file, it is going to it is going to execute your jar file as a MapReduce. So what it does, there are multiple phases. So it creates different phases. First phase of the MapReduce execution is a map phase. Then you have shuffle and sort, and then you have reduce. Right? So in the map phase, basically it creates multiple map tasks to process individual copy of your block. Once it knows that there are two blocks, it basically creates two input splits. So it by default always the splits are calculated based on the block. So number of blocks is equal to number of splits, unless you configure a different split size. So based on the input splits, job tracker is going to create two map tasks. If there are two input splits, it will create two map tasks, and it will decide which task tracker I should assign this map task based on the resource availability with that machine. So let's assume that it assigns map1 and map2 to these two machines, which are going to be executed as a separate JVM in these two machines, okay, and which are going to process data stored on this block. Right, and then excuse me, they are going to generate the intermediate output, and they will write this intermediate output in this files. All right. So what it does, the job tracker is going to basically create or assign the map task to different task tracker, and these map tasks are being executed in their own JVMs in separate machines, and they are going to process data locally stored on that machine and generate the output again in the intermediate output file in the local file system. Periodically, of course, each job tracker will also send the status update to the job tracker. Each task tracker sends a status update to the job tracker, and that's how basically they keep updating the map phase status. So that's how you know how much percentage of map task is being completed. Once map task is 100% done, once all of them say that we are done, then job tracker sends shuffle and sort. But before that, let me explain you this part. Here what we have done, map task is going to process every record of this file one by one. So what it does, it has to do a lot of disk IO. It reads the record, and then it actually split that, process it, and for that record it will write the output into the file. This is one disk IO, and one output it will write. After that, again it will, for another record, it will again write the data, write the output by passing that record in the output file. So for number of records, that many number of disk IO call it makes. Of course, it's not that many numbers, because map also will store some buffer. It will have its own internal buffers, and then after buffer gets full, it will actually spill over that buffer to the disk. So it will not do it as many number of records that many times. It doesn't do the disk IO, but still there are a lot of disk IO involved. Okay, for every block processing. So every map task is actually reading a file from the disk and writing the data into the disk for almost all the data that it is being processing. So there are a lot of disk IO. Apart from that, it will so this is just a map task. Once it keeps sending the status, once the job tracker gets to know that just a map task finished, by which only we have done multiple disk IO calls. After that, job tracker will actually use a shuffle and sort phase to combine all the output data, right? As we know, so it combines this intermediate output data in any of the machine. Okay, so it's not like that it combines it in this machine or this machine. It can be on any of this machine. It combines the data, and then it actually send this data to one of the machines. It stores in the temporary location the combined output result of both output 1 and output 2 file. So again, this combining process that we have understood, what job tracker does, it is actually reading this intermediate output file. So there is a disk IO involved in that. And this, in our example, I am just showing you two blocks. right? But there could be multiple blocks. That means multiple output file generated. That means multiple time disk IO will be used. So that many number of disk IO is involved, and it actually combines the data, and there are too many disk IO calls which slows down the performance, and finally it writes the data into the data node. So one of the available data node. So again, when you write the data, there will be a disk IO. So in shuffle and sort also, it's a heavy process where you have lot of disk IO calls. At the same time, you have also network IO calls. Lot of network transfer happens of the data, right? Because you want to merge the data from multiple machines. So there is this is the phase where it uses an algorithm called external merge sort, where it basically tries to combine the data, and it tries to kind of merge them in a single file. Once it completes that, then it sends that output to one of the machine, and that's how it stores it. So shuffle and sort also, heavy network IO and disk IO calls are made to achieve that combination, to merge that data. And once that is merged, then reduce phase starts, where job tracker can send a reduce task to one of the machines, so it will execute a reduce task on that machine to process this data, and reducer will also do the same thing. It reads the data from the file, again disk IO call is made, and then it will basically write the data into the output directory, which is your HDFS output path, which you have given here. Okay, in the command line itself you would have given output path, so where reducer is going to write the output data, again a disk IO call. So in these three phases, there are too many disk IO calls which are being made, and that's how entire MapReduce completes, execution completes. Of course, during the reduce execution also there is status updates sent to the job tracker by task tracker, saying how much percentage of reduce is completed. And once that is done, 100%, then that means your map and reduce are 100% completed. Your output is written. Then job tracker then executes a final stage called job completion, which basically informs job client that your job is done successfully, and at the same time it does some cleanup activity where it goes and cleans up all the intermediate output file, because only final output exists in the HDFS. Intermediate output file which is generated in the local file system are all cleaned up, deleted. Okay, so that's how a MapReduce execution occurs internally. Okay, but what I have highlighted here is just to make sure that everyone understand. Here lot of disk IO calls are made in every phase of map and reduce, map, shuffle, sort, and reduce, which is why performance wise it is not very good. Okay, and in what scenario it is not good, we will be talking about that also, but I'm just trying to highlight one key point here, which is too many disk IO calls, too many network IO calls also, which is being made here to complete some MapReduce execution. Okay, now why this is not good? Like, because you may say that yeah, it is still doing divide and conquer, so it is still doing faster compared to traditional systems, so why it is not good? So when we talk about iterative analytics, we'll understand what happens and why MapReduce cannot really scale to that level to do the iterative analytics. But anyway, so this is how MapReduce works, and I'm sure everyone agrees to this. So is everyone clear as of now? Anybody has any questions on this? Yes, Dishto, tell me. You want me to unmute you? Okay, okay. Yeah, you have a question. So Deepta has a question. The code runs on all the replicas or just one of them? It actually runs on only one of them, right? It doesn't need to run on all the replicas because then it's an extra processing and extra overhead. So it doesn't do that. It just runs on one replica. In case if there is a failure, for example, here, if this map task is failed while processing the block 1 data, maybe it could be failed because of some logical error in our programming. So it kills that JVM. So job tracker immediately sends a notification to task tracker that this is failed. So at that time job tracker will actually immediately send another map task 1 to another machine where the replica copy of block 1 is stored, and that's how it can process that replica copy in another machine. So the replication copy will be only used when there is some failure. Otherwise it will just process one copy. Is that clear? So, okay, on one replica, but maybe multiple node where blocks are available. Uh, so Satya, when we say replica, this is block 1, right? So this, as you can see from here, block 1 is here, block 1 is here, and here. This is called 3 replica copies of block 1. Okay, so which means these three replica of the same block will definitely be stored in 3 different machines. If you know rack awareness policy, right? In rack awareness policy, we understood that how different replicas can be placed in different machines in different racks. So it will always be stored in different machines. So that means I have 3 copies of block 1, but when I'm processing this file, which is divided in these 2 blocks, I will process only one of the copy, not all the copies. Only one of the copy will be processed. If it is successful, I'm fine. If it is not successful, I will use another one. Okay. Okay, Rajesh has a question. What is speculative execution? So Rajesh, speculative execution is basically a concept in MapReduce where what job tracker does is, let's say it has executed this map task. Let's say map 1 and map 2 are being sent to these two guys, task tracker 1 and task tracker 2, and they are being executed. Okay. Now there is a configuration property beyond which if the map task is not responding, I mean it's not completing, then it actually starts another map task. So what it does is, let's say if this map task is going to take a lot of time, then the configurable time to complete this task and process this data, then job tracker will create another map task and send it to another task tracker machine where the replica copy of that block is available. Okay, so another map task is going to process replica copy of that parallelly. Now what happens here, you have 2 map tasks which are same map tasks, which are basically 2 instances of the same map task, which are basically running on 2 different machines on the 2 different blocks of the, I mean 2 replica copies of the same block, right? Now what happens here, whichever completes first, let's say for example this guy completes first, it generates the output and it has given the status that I'm done. Then job tracker will consider this output and it kills this map task, whichever state it was, it kills that map task and deletes this output file. So basically speculative execution means it speculates upfront whether some task is going to perform very slow or if it is taking a lot of time to complete. It will just try to speculate it and execute parallel tasks, so that in case if that task will fail after waiting for a long time, it's a waste of time, right? So to avoid that, it creates another map task and send it to another machine. That is called speculative execution. Is that clear, Rajesh? Okay. Anybody has any other questions on this? Cool. Okay. So now let me show an example on MapReduce. You have done this, so it becomes very easy for you to understand. But I still want to cover this just to make sure that how do we actually process data on MapReduce, right? And what kind of limitations we have in terms of programming MapReduce as well. So that when we go into the Spark programs, we can easily understand that. So let me open one file. All right. So I'll be taking the same example which is very famous and everyone know, which is a word count problem. But we don't want to really understand how to solve that problem because I'm sure everyone knows that, right? So I just want to cover what happens behind the scenes. And then when we are going to solve this problem using Spark, we will see the difference in terms of what kind of benefits we get while writing programs in Spark versus MapReduce. So first of all, as you all know, right, we just understood MapReduce architecture, but we still want to understand this problem, how can it be processed using MapReduce. So let's say I have this file, right, and I'm just showing some sample data sets which has some certain words in this file, and I want to count the occurrences of every word. When you want to do that, you just take this file and store it in HDFS first, and then you write MapReduce to process that, right? So can we assume that this file is, let's say, stored in HDFS, which means it would be divided in 3 blocks or 2 blocks or whatever, right? We are just assuming that it is divided in 2 blocks, and they will be stored in, let's say, 2 different machines. So it will be something like this. Okay, these are my 3 blocks, and they are stored in 3 different machines: task taker 1, 2, and 3. Right? And when you write MapReduce and when you execute this program on this data, you know that it is going to create 3 map task instances to process this data, right? So basically, this much we all know, we are fine. Now map task is going to process these 4 lines of records in a block B1, this is block B2, and this is block B3. So each map task is parallelly processing this data, right? But here in MapReduce, what happens? So there is a fundamental principle in MapReduce that every data that you are going to process in MapReduce will have to be converted into first key and value format, right? We always use keys and values to process our data. Why? Because why do we really need key and value? Can anybody answer this? People who have already gone through MapReduce and used a lot of MapReduce programs. Why does MapReduce need your data to be divided into keys and values? What is the reason behind that? Okay. Um, Right, that's correct actually. So some of you have given valid point. So basically, during shuffle and sort phase, our fundamental problem is I want to do distributed processing. That is the reason why I have stored a file into 3 blocks in 3 machines, which are distributed now. But when I'm processing it, I need to consider all this data as because I still want to process everything together and then get the result out of it. So to do the distributed processing, you can individually first process them, which is fine. But then you need to also combine this output. Now that's the phase where you want to combine this output. You want to do some intelligent way of combining the data. And that's where you need, if you have divided your data in key value fashion, the combining process becomes simplified. So let me explain that. So for example, I'm sure all of you know that each line is divided into key value, and we take key as a byte offset and value as the entire record, right? So I'm not going into those details like how does it do it. I mean, you can just check it here. Like this is the pseudo code, like where it creates multiple instances of your mapper class, and then it takes every record in a block and then convert that record into key value format based on the input format class, and then pass it to your map function. That's done by internally by framework. We don't do this, right? So anyway, I'm assuming that all of you are aware of this. So every record is divided into key and value. So there will be key, which is a byte offset, value will be the entire record. So now assume that the first block is converted in this fashion. Now map1 is going to process that, and we know what we do in map logic. We take this record, we split them based on the word, based on the delimiter, take all the words, right? Iterate through them and then write the data. So we do something like this, right? That's if this is my line, this is my record. What I'm doing, I'm splitting it and converting them into the array of words. So you will have array of all the words which are mentioned here. Okay. Now what happens? You are basically trying to iterate through every array, every word in the array, and you are writing that output like word as a key and the value as 1, because we know, right, that we have to convert every data into key value, and then we can write it as an output from the map. So it's like apple 1, banana 1, occurrence of that word, and word as a key and the occurrence of that word as a value. If again apple comes, we write apple comma 1. We don't increment the count. We again write orange comma 1 and apple comma 1. Now why do we do this? So we basically write, let's say after processing all the records, we just keep appending the records like this. So we will get basically the output in this fashion, right? As you can see here, this is my output from map1, map2 and map3. For the space issues, I have just taken some sample key value pairs. So once you have written this completes your mapper phase, right? Here, as you can see, I have done my mapper phase here. So my map phase is done, where output of map1, map2 and map3 is generated. Then what happens in shuffle and sort? All these output files are basically combined. So this is the crucial phase, and that's where they actually wanted to do some intelligent way of combining this data. So what they do, they want to convert first the data in key value fashion. Why? Because for example, let's take this example, orange. There are 4 different records, orange comma 1, which comes as an output from multiple output files, right? 4 key value pairs of orange comma 1 is here in map1 output file, 2 are there in map2, 2 are there in map3. If I want to combine all this, then I can't append it. I should have some intelligent way of combining it. So what I do, I take key and all the values are combined for that key, right? So the fundamental objective of combining the data is basically, if you can divide it in key value fashion, which is, I'm sure most of you have worked on hash map objects, which is a data structure. It does that in order of 1 complexity. If you really know, if you can find out the hash code of a key, you can compare that key with any key and find out both are equals or not. Once you know that particular key, that yes, it falls under this bucket and it is equal, you can easily append the value for that key. So it is very fast. So in terms of increasing the in terms of achieving the effective time complexity, it mandates you to divide your data in the form of keys and values so that you can combine it efficiently this way. Okay, so all the keys and values are combined in this fashion, and then reducer is going to perform for every key and a list of values. So every key and list of value will be given as an input to the reducer. The reducer is going to take that and then process it. So we know, right, once a reducer takes this key and list of value, it will just go and take the sum of all these ones, and that's how the count is given, final count is given for that word. Similarly, for all the other key values, the reduce method gets called for that many number of times, and it will actually write this output as a final output file. This is how your problem is solved of word count, right? We know. But the challenge here is, as you can see, first of all, I always have to divide data in key and value. So there are some problems, some data which cannot be divided into key value. What people do in that, people actually create their custom objects, and somehow they create a dummy key or dummy value and custom objects as either vice versa, or key or value, and they try to solve that problem because they are trying to fit everything in MapReduce way, which is not really a good way of programming. Sometimes it is not needed to fit everything in MapReduce way. That is one problem. Another problem is, as we just understood, every key value pair which is being shuffled across a network. So I'm increasing too much network complexity here. Okay, I'm sorry, I'm occupying a lot of network bandwidth here, because all these key values will be transferred over a network, so there is too much network traffic which is being consumed. And apart from that, for even during the map phase also, you are processing for every record, you are trying to process it and write it into the output. So again, too many IO calls. So this also validates that too many IO calls and too many network IO calls are needed to achieve this, to basically complete these steps at every level. And that is also a problem. So you are actually trying to use lot of network bandwidth. You are trying to do lot of disk IO calls to complete one MapReduce cycle, just one cycle, which is map, shuffle, sort, and reduce. If I want to do many cycles like that, one after another, then you can imagine too many disk IO calls and too many network transfers have to happen. Right, so there is a lot of problems if you use that way. So this is one way of solving a problem, but there are flaws in that. One is programmatically you have to tie everything into key and value, which is not good, and another one is basically you need to kind of shuffle everything over a network, so it consumes a lot of network IO, it consumes a lot of disk IO as well. And the reason why I'm highlighting this point right now, because when we are going to talk about Spark programs, you should remember this point so that you can easily, compare between both of them, which helps you clear your, concepts on Spark. So is everyone clear as of now? I've just shown this problem just to help you understand like how, what happens behind the scenes for a MapReduce problem. Any questions as of now? Anybody has? So I'm not going to show you the program. If you want, I can show you. So do you really need to see the program for this? If required, I can show you, no problem. I can quickly execute that program. But I leave it to you guys. Okay. Cool. So I just got responses from a couple of people like who are responding and who are being interactive. So I just want to make sure that what about other folks? Like, are we following up? Is there any questions anybody has? Yeah. Okay. Cool. So that's where we basically wanted to leave with MapReduce. Okay. So let's understand now a little bit more on this MapReduce limitations which are there here. See, what are the limitations of MapReduce in Hadoop? So since we understood MapReduce, let's try to understand this. So it's unsuitable in real-time processing. Now, why do we really say that it's unsuitable in real-time processing? What makes it unsuitable? So being batch oriented, it takes minutes to execute jobs depending upon the amount of data and number of nodes in the clusters. This is just one line of statement. After that, there is no other stuff. That's the reason why I explain you that entire architecture, just to make sure everyone realizes this importance. For example, now this is one cycle of MapReduce to process word count example, right? Now what if I want to execute a MapReduce program using chaining of MapReduce program? I'm sure you would have gone through it in Hadoop class. What is chain of MapReduce? So let's say you want to complete one job. If you have executed high queries, you know that when you do some complex high query, like for example, if you write something like this, select, star from table, and then instead of from table you can just have inner queries, basically something like this. Here you just do select, then you do join, blah blah blah. So what I'm trying to highlight a point is, when you do all these queries, it actually in Hive it internally converts it into MapReduce, but it does convert it into multiple MapReduce jobs, not in a single MapReduce job. Depends on your query basically, but if you are having a lot of inner queries, then it tries to convert it into multiple MapReduce jobs. So it will be something like this. You have, this is your MapReduce 1, this is your MapReduce 2, and this is your MapReduce 3. For example, let's say there are 3 MapReduce jobs required. Once I complete this, then I get a result. This is my input data. Once I process via these 3 MapReduce jobs, I get the output. Okay, this is called chaining of MapReduce, right? After completing one MapReduce, the output is given as an input to second MapReduce. Then output of that is given to the input as to the input of third MapReduce job, and so on and so forth. Now imagine when you have this situation where you want to write multiple MapReduce job and process a data, which is this input data. Each map cycle, what it does: map, shuffle, sort, reduce, right? A map, shuffle, sort, reduce, and same way here also, correct? You have map, you have shuffle, sort, and you have reduce. So what is happening here? As you can see as a user, I am giving some input and I am expecting some output. I don't care what kind of jobs or what kind of execution that it internally uses to complete that processing. I don't really care. But if you see here, 3 different MapReduce jobs are being launched. That means 3 different cycles of map, shuffle, sort, reduce happens. Every cycle we know too many disk IO calls happens. At map phase, at shuffle sort phase, at reduce phase, and at the same time shuffle and sort phase also too many network IO calls happens. Again, that goes as an input to next MapReduce. That guy will do the same thing, right? So you can see that to complete these 3 MapReduce jobs and finally get the output which is expected, you have to go via too many disk IO calls and too many network calls, which drastically slows down the performance of the job that you are being executed, right? So now the question comes is, if I have a need where I am getting some real-time data, okay, when we say real time, what is the real time? First of all, real time means as and when the data comes. For example, Twitter. A lot of people take Twitter as an example, which is a good example. So as and when some tweet comes, I want to just take that tweet data, I want to analyze it for some various use case, and I want to calculate the output and generate the result, generate the prediction. So as in, it's like a continuous input of the data, Immediately as and when the input comes, you immediately process it and you generate the output. So it's like continuous input, process, input, process, output, and that has to happen very fast, because each real-time data you can't wait. I mean, if you want to process it, you have to process it faster and generate the result, and next thread has to wait for the next input record. So we are going to understand more about it in the Spark streaming, but I'm just giving you a high level idea. So there are, let's say, too many real time data which comes. Now there could be multiple sources. There could be Kafka as one message broker who pushes the messages on a real time basis. There could be some other real time source, you know, who can pushes the data. So it doesn't matter which is pushing the data. But then whoever is pushing the data, if I'm using MapReduce as a framework to process that, what happens? By the time I complete this execution of map, shuffle, and sort and reduce, many real-time data would have come. So I cannot match the requirement of real-time processing the data. Why? Because there is a fundamental problem with the framework itself. It takes a lot of time to complete map, shuffle, sort, and reduce only one cycle, right? It takes map, shuffle, and sort. It takes basically disk IO calls for map, shuffle, sort, reduce, as well as network IO call in shuffle and sort. So there is a lot of time being used to complete one cycle, and this is one of the reason why it cannot be a good candidate for real-time processing. You can't use MapReduce as a candidate for real-time processing, because real-time means it has to be in a fraction of second. It has to be processed, and next thread should be available to take another data. MapReduce cannot do that because of its challenges in terms of the way it processes the data. The way the framework is designed cannot support real-time, and that is why this statement says unsuitable in real-time processing. It doesn't have a capability to support real-time processing. Is this concept clear with everyone? So now, if I really need to, let's say, execute 3 MapReduce jobs, that means if I have chaining of MapReduce to process, let's say, to solve one use case in real time, I cannot even imagine to use MapReduce, because you can see every cycle it is going to take a lot of time. So by the time I complete one cycle using these 3 MapReduce jobs, I have already spent a lot of time, and that will definitely not be considered as a real time, right? So this is one of the reasons why MapReduce is not suitable for real-time processing. Is that clear with everyone, this portion? Okay. So now it says unsuitable for trivial operations. Well, this is, again, if you want to do joins in MapReduce, you have different join techniques like map side join, reduce side join, right? And I'm sure we have done a lot of programs on that as well. You know how to do joins in map side as well as reduce side, basically to join multiple files and process those data and then generate some output. So you have to write a lot of programs by yourself. So if you really want to do some complex execution using joins, you have to write that kind of keys. Like you have to create a complex keys values and then try to support it. So there is no the highlight of this point is basically there is no inbuilt support of joins in MapReduce. There are no API abstractions available in MapReduce which can help you achieve joins in a simplified manner rather than writing complex programs, right? We have seen that in reduce join, if you want to write a program, you have to write 2 mapper class or 3 mapper class based on the number of input files, 1 reducer class, and then driver program. So too many lines of code you need to write to complete one reduce join example. But the same code you can do it in a very less number of lines if you do it in Spark. We are going to do joins in Spark as well, but I'm just giving you an overview. So Spark has some inbuilt support of how to do joins. And Spark doesn't really work on a map, reduce, shuffle, sort basis. It doesn't have that flow. So, that's why it is more easier to work with Spark, and it has inbuilt functions available like filter and joins. which is not there with MapReduce. We should not compare it with Hive and Pig, because Hive has definitely a join query. You can write simple join query and you can use that. But internally it will be MapReduce. It is going to convert everything into the complex MapReduce programs and then execute it. So it will still take its own time. But in Spark, there are a lot more APIs available which can do it in a very simplified manner. MapReduce unfit for large data on network. Basically, this point tries to explain that even though it works on data locality principle, it cannot process a lot of data requiring shuffling over the network as well. Why? Because you occupy a lot of network bandwidth. So there is a concept called combiner in MapReduce, if people are aware, right, which helps you to reduce the network traffic. But even that can be used only in certain use cases, which if it doesn't change the output. So let me just show you here for the benefit of everyone. Just take this example and let's try to understand. So let's say this is the output generated by every map task. Okay. Now all this map task is going to send their keys into the shuffle and sort phase. Like for example, orange comma 1, if we take 4 times orange comma 1's transfer over a network from map 1, 2 times from map 2, 2 times from map 3 to the shuffle and sort phase. So too many network transfer. Now for example, if you have 1 million such words, 1 million times these keys will be transferred over a network, right? So too many network bandwidth gets occupied, right? So instead of that, if you use a combiner, which is nothing but whatever reducer logic that you write, you just execute that code at every mapper output. So what happens now? Instead of sending 4 times orange comma 1, I'll just sum it up locally here. Excuse me. Yeah. Instead of sending 4 times orange comma 1, what I will do is I'll just transfer orange. I will just add up orange comma 1 here itself. So it becomes orange comma 4. Here it becomes orange comma 2 and orange comma 2, right? So I'm locally adding up all the values for the same key before I transfer over a network. And then I transfer only this data over a network. So what happens now? Orange 4 2 2. It becomes like this, orange 4 2 2. And then it goes to the reducer, which is again going to get the same output. 4 plus 2 plus 2 is 8. So your final output is not changing. But what you are trying to do, you are reducing the number of bytes which are transferred over a network. You are actually reducing the network traffic with the help of combiner. So that's the function or concept which is used in MapReduce to reduce the number of bytes transferred over a network, right? Now, you can just use the same reducer logic as the combiner logic in your MapReduce program and it solves this purpose, right? So total number of bytes which are written over a network will be reduced in this fashion. That's the use of combiner. But combiner can be used only in certain scenarios where the rule is you can use combiner only when the operation is commutative and associative, which means it should not change the final output when you use a combiner. See, in this case, I make orange comma 4 2 2, but then finally the output is still orange comma 8. So I'm not changing. Even if I apply a combiner at locally on every mapper task, my final output is not changed. That means I'm safe. That is good. But if you apply a combiner on every local mapper output, and if it is going to change the final output, then you should not use a combiner. So let me give you an example in which scenario combiner cannot be used. So let's say you have a big file of huge numbers. Let's say 10, 20, 30, 40, 50, 60, 70, whatever. I mean, I'm just giving some numbers. And let's say you want to find out the average of each number. Okay. So let's say these are the 4 numbers which are output from map 1. These are the 3 numbers which are output from map 2. Okay. There is a constant key for everyone, right? So they can be combined at the later stage. So key will be, let's say, K, K, K here. You can do this. You can actually have a same key for all the values. You can make this way. I mean, there are a lot of interview questions where you may need to use constant key for solving some problems like this, if you want to find out average of all the numbers. So that what happens in shuffle and sort, all the numbers will be, grouped like this for the same key, so that it goes to only one reducer where you can process all the data and get the final average, right? So to make sure all the data goes to one reducer, you should have only one key. Anyway, this is not the point. The point was I wanted to explain that let's say there are 7 numbers and I want to find out the average of this number. So I am taking an average. Let's take combined average. First calculate the sum of everything and take the combined average. What should be the average? So if I just say 70, 90 and 100, 150, 210, 280, 280 by 7. 280 by 7 is the average, right? Which is 40. This is without combiner. Now if I use a combiner, that means the same reducer code if I use at every mapper output, I'll take average of these 4 numbers. What is the average? 100 by 4, which is 25. And this is 180 by 3, which is 60. Now these 2 numbers are transferred over a network to the reducer. So now what happens? 60 plus 25, again you get the average of this, which is 85 by 2, which is 42.5, right? So this number does not match with these numbers, which means if you use a combiner in this problem, it is going to change the final output, right? That's the problem. So you need to be always certain, and you need to make sure that if you use a combiner, it should not change the final output. If it changes, you can't use a combiner, right? So this was the fundamental concept behind a combiner. I just wanted to explain, just to explain that point which I'm coming through. But are we clear as of now? Anybody has any question on this? I can't go and programmatically explain this because I'm sure this would have been covered in your Hadoop class. Okay. So Satyanarayan, basically what I'm doing is, you want me to explain combiner, right? Like do you want me to explain this example, this where it cannot be used? Okay. Right. So what I'm doing is, let's say we want to calculate the average of all the numbers in a file. There are 7 numbers in a file, for example, and you want to calculate average of these numbers. If you want to calculate average of these 7 numbers, what do? Just, let's say these 7 numbers are output from 2 mapper tasks. Okay. So 10, 20, 40 and 50, 60, 70. They will be combined in shuffle and sort phase. Since they have same key, all of them will be grouped like this: 10, 20, 30, 40, 50, right? And then it goes to the reducer. Now reducer, what it does, you would have written a logic in reducer which just iterates through all these numbers and take the average of this number. That means take the sum and divide by total number, which is 280 by 7 is 40. Right? So this is without combiner, you are getting this. Now if you use a combiner, when we say combiner means I need to use the same reducer logic at every local mapper output. So when you do that, it is again going to, let's say, take the average on internally on every intermediate output of mapper task. So that means you get 25 and 60 as an output. And that data again you are transferring over a network to get the final average. So your average is 42.5. So this time, because I wanted to reduce a traffic, I use combiner, but it is changing my final output. So this is the case where you should not use a combiner. So when you are using a combiner, there is always a limitation: when to use a combiner, when not to use a combiner. Is that clear? Okay. Anybody else has any question on this? All right. So basically, unfit for large data on network is what I wanted to cover. So here even when you apply this combiner, right? First of all, combiner has its own limitation. It may not work if your final output is changed, as we understood right now. And even if you apply a combiner, even after that also, let's say a lot of data are being transferred over a network. In some cases, let's say you can't use a combiner, as we just saw. In that case, anyway, network traffic will be higher. So those are the problems. Those are the use case where if too many network transfer happens, too many network bandwidth, you consume during shuffle and sort phase, then anyway MapReduce is not going to scale. It is not going to, it will sometimes crash the memory and crash the output itself because it is unfit for large data processing over network. So that is also one challenge. However, MapReduce has its own internal buffering concepts where it tries to buffer only those data which it can fit in memory, and remaining it spills over the date. Yes, Vikas, you can do that. That is a valid point, but I'm just saying that where you can use a combiner, where you can't. We can always discuss over the different ways of solving that problem. Your thought is valid, but I'm just trying to highlight a concept of combiner, and I'm just trying to highlight a point that even with combiner, sometimes you cannot use that concept, and in those cases you will have too many network transfer over, too much data transfer over a network, and that's where again MapReduce performs bad. It doesn't perform well. Okay. Unsuitable with OLTP. So OLTP requires a large number of short transactions and it works on batch-oriented framework. So as we mentioned here, it is unsuitable with OLTP means what? In OLTP, we want to complete. I mean, we are working on a transaction levels, right? So I mean, the lot of transaction data that comes, and we want to kind of do that in a faster manner. You want to search the data in a faster manner. So again, that need of faster processing comes here. Whereas in MapReduce, you can't do it because there is no concept of indexing. You can't index the data on HDFS, right? MapReduce always go to the disk and process the data. So there is no way of improving that performance. MapReduce doesn't have any internal concept through which you can improve that performance. So that's why it is basically it's a batch oriented analytics framework, and hence it cannot solve that problem as well. So when you want to do a lot of ad hoc query analysis, which is called interactive analytics. When I say ad hoc query analysis, I'm sure you all have used Hive. When you log into Hive, right, you will write one query. Let's say you want to join 10 tables, but you know that you can't join all the 10 tables together. One problem could be that heavy data load. Another problem could be that they are not joined by themselves. You need to join in a phase by phase manner, stage by stage manner. So let's say you join two tables. You write one query, you get the result, you analyze it, and then you say, okay, let me join it with another table. Then you analyze it, you find some data you want to clean up, you just filter out some data using where group by query, and then you want to join that with something else. So when you are doing this, what you are doing exactly, you are doing ad hoc analysis. As then when you execute a query, you get the result, you analyze that, and then you refine it, and then perform one more operation on top of that. This is the typical job profile of data analyst. All the data analysts in the world are doing this. They are basically analyzing the data on an ad hoc basis. They fire some queries, and it doesn't mean that only SQL queries. They can fire any analysis logic. They want to get the output, they see the output, analyze it, and then they try to refine it by writing some other analysis logic. Now this ad hoc analysis is very slow when you use MapReduce. All Hive queries, if I want to join 10 tables, I have to wait. I mean, I can go for a coffee and come back and still it will not be done. Based on of course, the volume of the data. But then because it does all this, map, shuffle, sort, reduce cycle, it uses all the disk IO calls, it will never be completed in a faster manner. So that was also one more major motivation behind developing Spark. Ad hoc analysis was very slow. That is called interactive analysis. So tomorrow I'll be presenting one white paper to all of you. There we will see all these things in detail, but that is one more reason. This is not a reason, so let's ignore this. This is not really a reason, so I don't want to comment on that. Unit for processing graph. By the way, there is something called Apache Graph Library, Giraffe Library, which is available to process graph using MapReduce. But it adds additional complexity on top of MapReduce. And again, all the Giraffe libraries are basically having its own APIs, which we need to be converted in MapReduce. So again, it's slower when building graph and working with graph. If I want to find out shortest distance between two nodes in a graph, it will do a lot of calculation, lot of computations, even on a distributed nodes, and it slows down the performance. Whereas the same thing can be achieved in a faster manner using Spark, and Spark has its own graph API called GraphX, through which you can do it in a faster manner. And a most important advantage, or I would say not advantage, but most important reason or motivation why Spark came into existence is because of iterative execution. Okay, we'll be understanding about iterative execution. So iterative execution is basically, I think we have seen this example where, let's say, I have multiple MapReduce job, map 1, 2, 3, and they have to be executed in one by one cycle. Now, if they want to execute it in this order, then it is called iterative, right? I'll first execute MapReduce 1, then I'll execute. So this is actually not an iterative, by the way. This is chaining of MapReduce, but iterative analytics is also similar to that. So what I will do is, tomorrow when I explain this iterative analytics, I will explain it using one clustering example of machine learning. Okay, I know many of you are not aware of machine learning, so don't worry. I will not get into the details of that right now, but I'll take one clustering example just to help you understand what do we mean by iterative analytics. And once you understand that, you will easily understand why MapReduce is not fit for that and why we need something else like Spark to solve that problem. Right? But ultimately, the fundamental reason why MapReduce is not suitable there because of the disk I/O calls and network I/O calls. It slows down performance drastically. So these are some of the fundamental reasons why MapReduce is not performing better, and you need an alternative solution, which is of course Spark in our case. So what is batch and real-time processing? We have already understood. But the example is, real-time processing example is fraud detection. I mean, credit card or debit card fraud detection is one of the real-time example. There are many other real-time examples these days, like stock exchange market is real-time analytics. I mean, there are companies available who does a lot of high frequency trading stuff, right? There is something called high frequency trading algorithm. So what they do is they write this algorithm, and as and when the data of the stock price fluctuates, immediately it calculates the next price which is going to be in the next 1 second or whatever time period, and it predicts it to all the investors. So investors will buy that stock or sell that stock based on that prediction. So it all happens in real time. That is one more use case of real-time analytics. That way, Peter streaming is another real-time analytics. So there are a lot of real-time use case, and in fact, entire world is now going towards real-time analytics. In fact, everybody who is doing batch now are going to do real-time also in future, because that's the fundamental objective of this entire frameworks or usage of this big data stack. They want to process big data and analyze it in a real-time manner rather than batch. So initially there was a batch, now everybody is moving towards real-time. So we have just given one example called fraud, but there are likewise many examples where you need this real-time. Batch processing is a regular report requiring decision making, and also any historical data processing that you want to do, you want to analyze it, and then you want to generate some reports, you use basically batch processing. Okay, so yeah, this is something which we have seen, and I told you that there is something called Spark Core, then there is something called Spark SQL Streaming, MLlib, and Graphics. So basically, just 1 second. This is how you visualize the Spark ecosystem. This is Spark Core. Okay, this is the fundamental Spark engine. Everything boils around to this. So you need to basically understand this very clearly. It also contains concepts of RDDs. Ideally, this should be part of this. All the other components are basically ecosystem components which talks to Spark engine. and they have their own functionalities. As we know, Spark SQL, you can write SQL and use Spark engine to process the data, structured data. Streaming will be doing for analytics, real-time analytics. MLlib is for machine learning library, and GraphX for graph processing. Okay, so yeah, there is a usage written here. So history of Spark. So we understood the motivation behind Spark, like why Spark has been developed. Why there was a need of any better alternative than MapReduce. So we understood some of the flaws, some of the challenges with MapReduce, and now we are going towards what is the other alternative. So Spark is definitely one best alternative we have. So we are going to learn about it now. No, Deepak. Hive and Pig are the components for MapReduce, which means Hive is developed where if you don't want to write programs in MapReduce, you write it in SQL and then internally, basically SQL using Hive. So Hive engine converts that SQL in MapReduce and then process the data. Similarly, Pig script will convert your Pig Latin scripts into MapReduce and process the data. Scala you cannot compare with Hive and Pig. Scala is not a component, it is just a programming language. So you write so maybe let's say SQL can be compared with Scala or Pig Latin can be compared with Scala, right? It is just a programming language. For Hive, there is a equivalent component in Spark which is called Spark SQL. And there is also going to be a support available in Spark for Pig, right? So is that clear now? Okay. So history of Spark is explained as below. So as you can see that 2009 time frame where they started, and that's where I am going to present one white paper which is from this guys, started at UC Berkeley MP Lab. They started this white paper, they presented this, started that why the Spark is needed, what are the motivations behind it, and what kind of fundamental changes they have made in the framework to make it 10 times faster than MapReduce on a disk and 100 times faster on memory. Then by 2010, it became open source. 2013 project was given to Apache Software Foundation and the license was changed to Apache 2.0. And 2014 it became top level Apache project where it was officially used in production by one of the company called Databricks. So Databricks are the primary promoters of Spark, by the way. They are the ones who have used it extensively. And by the way, they set a world record in large scale sorting in November. They used Spark to sort large number of data across distributed nodes, about thousands of nodes. I don't remember the statistics here, but yeah, they have used this Spark framework to sort billions of numbers using this big cluster, and they could do it in some few seconds of time, whereas MapReduce was giving a lot more time, and there were other frameworks also could not do it in that time. So they won that. They set a world record basically using Spark. And yes, at present, it exists as a next generation real-time and batch processing framework. So it is definitely going to be a very hot technology in terms of processing the data in a distributed manner, and a lot of companies are going to use that in their production environment. So I can say you all are on the right track. This is definitely going to be used in all the big data setups. Okay. So yeah. Now I will just keep it this way. I just want to pause it here. We will definitely go and understand a lot more detailed architecture about Spark from tomorrow onwards. But what I have covered so far is basic backgrounds of HDFS, MapReduce, and then we understood the motivation behind Spark. So is everyone clear as of now? Anybody has any questions? Yes, can you please drop me a mail? I'll respond to that. Is that fine? Okay. Just give me 1 minute. Dipta, I'll be giving all these details when we come for a Scala course. No, Narendra. It will be the same cluster. You can use Hadoop and Spark both. So I have opened a poll. If you don't mind, can you please fill up this poll survey? This is just one formality that we need to do. I could see 3 people have not yet completed. Can you please fill up fast? Okay, so everyone, this is just a information I want to share. I'll be sharing all the details tomorrow, like how to install Spark and how do you make it as a cluster and everything. So don't worry about it. I'll be explaining you how to install Spark tomorrow. I'll be sharing that guide also with you. It's very simple, so you can easily work on that. Satya, yes, I'll be talking about certifications in the coming up sessions. Okay, Narendra, as I said, Spark can support both batch and real time, so you don't need to worry about, you know, I mean, having them install as a separate environment, like one is Hadoop, one is Spark. You can install Spark on the same cluster where Hadoop is installed. Then only you can use HDFS to process the data, right? So Spark needs to be installed on the same cluster. You can also install it as a separate cluster and make it point to this HDFS, but there is no need actually. You can just install it on the same cluster. So we are going to use one cluster which has both Hadoop and Spark. Is that fine? Yes, because I'll be sharing it tomorrow to everyone, where you'll be getting all the mails, subsequent mails from me. All right. So, any further questions anybody has? Well, Dipto, I don't normally share that. But anyway, you can just drop me a mail. I'll share it over email. So Narendra, is it okay if you can wait for some more time? Because let's understand Spark first. Let's understand the architecture or concepts of Spark, and then we will be understanding Spark SQL, right? You will, I mean, it will not be tomorrow, but when the time comes, you will automatically understand like why you can, where you can, increase the time where, your high queries were taking a lot of time, but Spark SQL can do it in a much faster manner, right? So you need to understand all these ecosystem components like Spark, Spark Streaming, Spark SQL to achieve your requirement. Once you complete that, then you can easily visualize like where which component can fit where and how do I transform this data into these components to make it faster. Okay, anybody else whose question is not answered, please let me know. All right, great. So that's all I had for today's session. Thank you everyone. I hope all of you have enjoyed this session. We'll be having a lot more fun tomorrow when you start unveiling Spark and understanding Spark architecture. You'll feel much better tomorrow when you completely understand that part. So thank you everyone and have a good day. We'll see you tomorrow. And good night for all the people in India.